Okay. Okay. So I want to reiterate what Celestine said. Thank you so much for spending your precious time in Barcelona attending our tutorial. We're very, very grateful. My name is Tijana Zrnic, and I am a postdoctoral researcher at Stanford, where I'm affiliated with Stanford Data Science and the Department of Statistics. So before we jump in, we just wanted to give you a quick overview of our schedule for today. So the tutorial will roughly be split into 3 one-hour blocks. The first 2 will happen before the coffee break, then we'll break for 30 minutes. We'll obviously stick around, happy to talk during the break. And then we'll be back for another hour. So at the beginning, we'll give an overview of the motivating applications and examples that really led us to start thinking about this area and to try to formalize it mathematically. Then we'll describe the mathematical framework that tries to capture all of these motivating examples that we'll see at the beginning. Then we'll talk about performative stability that we'll see is a natural equilibrium concept that emerges from this framework. And we'll talk about retraining as a natural heuristic to tackle these performative effects in practice. And we'll see how performative stability relates to retraining. Then in the second part, we'll move on to performative optimality. So we'll see that that's essentially the main notion of optimality in this framework. And we'll talk about how performative optimality relates to performative stability. And then we'll talk about 2 different families of methods for finding performative optima, in particular model-free and model-based methods. Then we'll break for coffee for about half an hour. And then when we're back, we'll first talk about some extensions of this basic framework that we'll talk about in the first part. And then at the very end, we'll talk about applications of all of these ideas, primarily in the context of economic markets. So we'll talk about power, we'll talk about what role incentives play when discussing performativity, and finally, we'll talk about digital activism. And then at the end, we'll give a quick summary. We'll discuss a few open problems and challenges. And then we'll basically just leave time for an open-ended discussion at the very end. Yeah, so just before we move on to the technical content, I'll just say that our goal for today is to, first of all, communicate that there is something very important happening when thinking about performativity. There are a lot of both theoretical and practical challenges that we're seeing. And so we're hoping that you'll see ways that as a community, we can all contribute to this field. And we'll just give a very brief introduction to this mathematical framework. Of course, because Celestine and I have both worked in this area, of course, the content that we'll present will in some ways be biased towards things that we personally like or that we're most familiar with. But we're also happy to talk more offline if you're interested in like particular aspects of this problem. We're happy to point you to any relevant literature that we think there is. Yeah, with that, I think I'll hand it over to Celestine.
Cool. Thank you so much. So yeah, let's jump right in. I want to start with an observation, which I think is very fundamental to everything that we're going to talk about in the following. So predictions in the social world are different from predictions in physical systems. So as an example, think about astronomy. If you want to make predictions about the trajectory of a planet, your goal is to detect regularities in nature's physical laws, and you try to describe this system as accurate as possible. If you succeed, your prediction will be accurate. So it's purely explanatory. You try to describe and understand the system. In social context, it's often very different. So predictions are often an intrinsic part of the system. They inform decisions, beliefs, and impact outcomes. So prediction is no longer a purely descriptive endeavor. I'll explain that more through examples in the following, but I think this is a very important conceptual takeaway here. So the first example I want to start with is election prediction. So let's say famous websites in the US, they publish polls and predictions about outcomes of elections. These predictions change expectations and beliefs of individuals, and they can impact outcomes and voter turnout. So they decide, people look at these polls and then they decide what to vote, and they decide whether to turn up for vote or not. This is a very fundamental observation that dates back to, I think there's a work here by Herbert Simon from 1954, where he's been studying bandwagon and underdog effects in election prediction. So a bandwagon effect is like this effect that people look at others and to determine appropriate behavior. So if they, especially in uncertain situations, if they see what others are doing, they follow. They're much more likely to vote for someone who's expected to win. The underdog effect is the other way around. So these phenomena have been studied in psychology and sociology for a while. Here's another example. What you see here is the distribution of poverty scores in Colombia. It's about 18 million people. And the origin of this poverty score was that there was a law in the early 90s that they should spend more on social programs. So they got priority for sort of prioritizing social programs to target like the poor in the population. So they were going out to collect data to develop this poverty score, which is a prediction of who's in need for support, basically. And then they used these predictions to allocate benefits. And what happened is that people adapted and statistical regularities collapsed. So at the beginning, it was mostly about politicians timing data collection to get like favorable outcomes for these poverty score calculations. But then as time passed, it's more and more turned into corruption, and we can see how the distribution has changed. So there's this sharp discontinuity at the threshold, which is 47 here. People were strategically behaving to be below the threshold to get the subsidies. We see similar effects in finance. For example, option pricing theory is sort of famously related to some of the financial crashes. And sort of this claim here by Donald McKenzie and Milo says that option pricing theory succeeded empirically, not because it discovered pre-existing pricing patterns, but because it pushed the market to conform to its predictions. So there were these models, these financial models to predict prices, and people started acting upon them. They used them to make decisions for investments. They also used them to think about markets. The parameters that appeared in the model were the parameters by which they were like thinking about markets. So they have some really fundamental effect on the financial economy as a whole. This distinction between social and physical prediction has been made in Oscar Morgenstern's habilitation in 1928. So his work was on Wirtschaftsprognose, so it was written in German, and he very well articulated this difference between prediction in the social world and prediction in physical systems. And he said that the difference is that in physical systems, there's no causal relationship between the prediction of an event and its occurrence. So he also points out that forecasts that can impact the predicted event constitute one of the most fundamental problems in the theory of economic forecasting. So it's like a very fundamental thing that these predictions impact people, impact behavior, impact outcomes. And it's interesting because it's also sort of fundamental to the endeavor of game theory, for which Morgenstern is known for. So in his later life, after his habilitation, there's this famous work he did with von Neumann about game theory. And it's also about actions impacting people, actions having consequences, and taking this into account. So this sort of loop is fundamental to a lot of the problems we've been thinking about in social contexts. So what about machine learning? We also routinely make predictions in social contexts. So here's an example from Silo. So Silo, if you go to their website, you can see that they use deep neural networks, complex models to predict these sad estimates for housing prices. So Silo is a retail platform for like properties. They estimate the value of houses. They publish these values that take into account a lot of factors about the economy, about the property, about just all the data they have to predict these estimates. And it has been shown that it's discussed very often that they set expectations in these markets and they impact sales prices. Another example is Google Maps, right? I think a lot of you use Google Maps if you want to go to a place, and Google Maps makes predictions about time of arrival, so traffic predictions. Imagine everyone following Google Maps recommendation, it will actually change traffic patterns. So there's also this feedback effect here. And of course, in recommender systems, we have it. So for example, this Discover Weekly uses some personalized playlist recommendations, and it will impact what you watch. It filters information for you, and it impacts clicks. Okay, now we have all that. We said that prediction in a social context has these causal effects, and we have these machine learning models being deployed in a lot of social settings. But how do we do prediction in machine learning? So here's the standard supervised learning paradigm. We represent the population as a data distribution over feature label pairs. We parameterize the predictive models with a parameter vector theta, and then we find a good predictive model through risk minimization on average to minimize loss on average across this distribution. And what's sort of intrinsic to this problem formulation is this static description of the world. So we have data sets about recommender systems, the famous Netflix price data set. We have data sets about risk scoring. We have data sets about other like social prediction problems. And we apply this paradigm to it routinely, just often without thinking about it. And I think what's interesting here is that we don't really have a language to articulate this difference between social prediction and prediction in the physical world, right? We assume that X and Y are sampled jointly from a fixed distribution. So there's no way any decision based on X prediction based on X could impact Y. So it's a intrinsically static description of the world. And everything that shifts is assumed exogenous to the system. And so the goal of performative prediction is to extend this classical risk minimization framework to account for the causal effect of predictions on the target of prediction. So the term performativity has been an established concept in economics, finance, and public policy, also in social science research. So it came up in various places, mostly in like economics, about how economic markets are sort of embedded in economics as a whole, and how these financial models shapes markets. And the overarching goal is to bring this concept of performativity into the foundations of machine learning, just from the ground up of how we think about ML, incorporate these social feedback loops. I think that's the one endeavor. Is the motivation clear? Are there any questions up to here? Then let's talk about the framework. So the thesis of performativity is that prediction can have a causal influence on the world that they aim to predict. So in machine learning, the lens to the world is the data. So if the world changes, it's going to surface as a distribution shift in our problem. And so we introduced this concept of a data-dependent distribution, a d of theta, which is the distribution after deployment of a model theta. And then we can estimate the risk of a model on the distribution that surfaces after deployment. So every time you're going to deploy a model, it has an impact on the environment, and you're going to evaluate its risk on the distribution that you have after you deploy the model. So we will expose these two arguments in the risk. So there's the theta that appears in the loss, the model that we're fitting, and then there's the d of theta, so the theta that impacts the data distribution. We'll have this notation to decouple these two angles, where the second one, what's in orange here, usually assumed to be static in a supervised learning setting. And we'll work with this very simple abstraction, which will turn out to be very powerful to talk about a couple of conceptual takeaways. And for simplification, we'll sometimes in the slides use C for like the data point, which is an XY pair. So the model can impact X and Y. So it can impact the distribution, features, and labels. It's like general in that setup. Yes?
Probably from a critics standpoint. So the theta that for it is minimal the risk, but not the theta is
yeah, that's a great point. We'll come back to that. For now, assume that there's a model and a distribution. It's the most simple abstraction you can have to talk about this concept. We'll talk about extensions, but that's a good point. Statefulness or sort of long-time dynamics is something that we're gonna come back to. So let's start with the most basic heuristic that we might use in machine learning to address distribution shifts. So we collect data, we see that things have changes, we update our model. So you can think of a standard, a very simple risk minimization, repeated risk minimization algorithm. You observe data, you optimize the model given data, you deploy it, induce a new distribution, and you repeat. Just for more like an optimization viewpoint, you have a distribution, it induces a loss function, you optimize on that distribution, you deploy, and you're going to see a new problem in the next run, a new distribution. And this sort of procedure gives rise to a natural equilibrium notion, which is if retraining converges, it converges to stable points, and these stable points are points, so models that remain optimal after deployment. Sort of a fixed point of this procedure. It's a very natural solution concept that we have in performative prediction. And you can now ask all sorts of questions about it. When does retraining converge? When do these points exist? This is all unclear a priori, right? Whether this procedure will converge and whether these points exist or not. So there is an assumption that we will work with. If you don't constrain the distribution map, basically everything can happen. So this is a regularity assumption on how the distribution responds to your model. And what we use here is we call it sensitivity. It's the assumption that if you change your model by a small amount, the distribution also changes by a small amount, some Lipschitz condition. And we measure distribution distance using Wasserstein distance and the change in the model in parameter distance. And under this assumption, you can prove convergence of retraining to these stable points. So more concretely, if we assume that the loss is strongly convex and the beta smooth in the data, so the gradient is Lipschitz in the data, then retraining converges to a unique stable point as long as the sensitivity is small enough. And convergence is at a linear rate. And so the intuition here is that as long as the problem is close to static, retraining basically converges. The sensitivity gives you a notion for how dynamic your problem is, how far away from static your problem is. Yeah, we can see if it's more strongly convex, you converge faster. If the sensitivity is smaller, you also converge faster. So it's kind of a contraction argument. I'm going to go through the proof sketch because I think this is like one of the interesting first and kind of core results in the field that show you a bit how you move from the static view of optimization to optimization in this dynamic environment. So the intuition is that in each step, you're solving a static optimization problem, as we are used to do. Strong convexity gives us a lower bound on the progress that we make, given the step size that we took in parameter distance. Standard strong convexity argument. But now what's special is that this theta k, the point that we started from, so just to recap the notation. So Lk is the loss on dk. So at step k, We observe decay, and then there's a loss function. And then we take a step on that loss. And the point is that this theta k is not just any point, but it's the optima on the previous distribution. So we can use this to relate the loss across two different distributions. And if we use smoothness, we can bound the gradient of a point in expectation onto two different distributions using the Kantorowicz-Rubinstein duality theorem. So we are taking the gradients or the gradient in a product with this vector. We bound the difference in expectation across two different distributions, and we can see that it's upper bounded by the smoothness, which is beta times the norm of the vector, times the Wasserstein distance between the two distributions. And the nice thing is that the gradient, we know that the gradient on the previous distribution was 0 because it was the optimal point. If we combine these two upper and lower bounds, we can see that we get the following bounds, and invoking sensitivity, we can now relate that to the parameter distance and get the sort of contraction argument. This is a proof sketch. It's meant to show that you converge under this condition on epsilon. For getting the rate, the equations are a bit more, it's a bit more notation heavy. That's why I've chosen to present this one. But it's like the idea is this contraction argument that the progress you make in the optimization step needs to be larger than what you lose by the shift you cause due to your parameter update. That's sort of the basic assumption. Yes. Yeah. So strong convexity is defined with respect to the parameters of the risk, and smoothness is the Lipschitzness of the gradient with respect to the parameters in the data.
Yeah.
Yes, to the parameters. Yeah, so we should, it's the smoothness, it's with respect to the data, it's the gradient with respect to the parameters. You look at the gradient and how much does it change with when you change the data. So it's sort of Lipschitz in changes of the data, but the gradient is taken with respect to theta.
Strong convexity is totally.
Yeah, you sort of, yeah, it was not very precisely defined. It was intentional, but you can go to the paper to see the exact definition. It's a bit of a non-standard notion of smoothness. Lipschitzness of the gradient, normal gradient with respect to changes in the data. Yes?
You need strong
You need, for this argument, you need strong convexity, which is kind of interesting, right? Because every time you move in parameters, you need to guarantee that you reduce your gradient, that you make progress. This is essential here. Without strong convexity, if any of these three assumptions are not satisfied, you can find a counterexample. So any individual assumption is necessary. Smoothness, strong convexity, and this Lipschitzness of the distribution. Against convergence, you get oscillation.
And it's also worth mentioning, related to that, is that this threshold of again over beta is also so even if you violate it, you still have sensitivity. Like you can have strong convexity for the sensitivity, but if you're at the threshold of again over beta, then you get regulation.
I guess you can tolerate some noise in the mapping from the parameters to the distribution.
I mean, the noise, we're not making an assumption on that mapping, right? That the mapping is just happening.
Yeah. What is the mapping? So because the population wanted to information.
I agree. Yeah, we'll get to different models and ways to model it. Yeah, but for now, we're just, you do retraining, right? The things happen naturally. You just respond, you just observe what's happening and you repeat your optimization procedure. And this is a condition, this Lipschitzness is a condition on the distribution map under which this retraining procedure converges. I think that's the claim that we make here. Yeah, so what's interesting, what I want to mention here is that these sort of fixed point arguments have appeared in like historical arguments about the possibility of public prediction. And they also used Brouwer's fixed point theorem. So by public prediction, they were talking about predictions that you make public, right? You don't just do private prediction in your office, but you release them in an economic context. That's exactly the case where you will induce performativity. And this here is like a very early argument from Simon about the possibility of election prediction. So you assume there's a response function, that the outcome is a function of the prediction. And then you can show this graph where you have the predicted value on the x-axis and the outcome on the y-axis. Let's say they are bounded between 0 and 1. It's the probability of winning an election. And the argument he's making is that if I predict value 0, I get a value between 0 and 1, somewhere on the vertical line on the very left. If I predict value 1, I also get a value somewhere on the line on the very right. And now if this response function is continuous and I draw a line connecting these 2 points, I somehow have to cross the diagonal. And this point on the diagonal is where my prediction is accurate after the response. So y hat is equal to y. It was sort of like a very basic argument, or it was like very fundamental. It's a simple like fixed point argument, but it was very fundamental argument to economics. And Herbert Simon, he also won the Nobel Prize for this idea of bringing psychological ideas into like economics and prediction. Just kind of, I think, an interesting connection. And so performative stability is a natural analog to these sort of fixed points if you think about it in a parametric setting. This here was only about existence. The previous result goes a bit further because it's a constructive argument. Good. Let me say a few words about the sensitivity assumption. So when is it satisfied? Is it sort of a natural thing? I just want to argue that I think it's pretty natural. There are a couple of examples where it's satisfied. Of course, it's not always satisfied, but it's not a vacuous assumption. So here's a simple toy example of estimating a binary outcome. So you make a prediction, you fit your theta parameters to predict based on the features, and you assume the outcome is binary, and it has like a bias. It's a self-fulfilling prophecy where you bias towards the prediction. Just a simple model for a self-fulfilling prophecy, and in that case, the epsilon is exactly the sensitivity in this definition. Independent for the distribution of x. Maybe a second example is if we recall this poverty score example from the beginning. Let's say you have a population of individuals in the threshold and you give subsidies to those below the threshold with the goal to move them further to the right, higher values. Yeah, so poverty score, just higher means better. So now if you move that threshold, you're going to impact a different part of the population, right? If you move it up, you have more people. If you move it further up, you will impact even more people. And I think here the sensitivity parameter corresponds to the fraction of individuals that are impacted by a unit change in theta. So if you change the decision boundary a little bit, you impact only a few people. I think that's sort of the intuition of sensitivity, which makes me believe that it's sort of reasonable in certain settings. Good. Any questions for that? So you're asking why stability is the solution we care about. Yeah, we'll come back to that. I've not claimed that. I said stability is a very natural equilibrium concept in this framework. In a standard risk minimization, you wouldn't have a language to articulate any difference between these solution concepts in the first place. But the second part of the tutorial will be about the different solution concepts. So now I want to just talk about retraining heuristics. So what we talked about, this retraining procedure was an oracle procedure. So we sort of assumed that in every step, we can optimize the risk on the data distribution. We know the distribution and we can optimize it. In practice, you usually only get samples from the distribution. And you also don't really do exact optimization. You do some sort of gradient descent or stochastic optimization as a natural concept. And there are several extensions to the framework where these more sample efficient and computationally efficient methods have been studied. And it's sort of interesting to see that a lot of the intuition carries over. So you still have fixed points as stable points as natural fixed points under these heuristics. And I think I want to go through the intuition of the SGD result, because that's sort of I think the most natural heuristic to do. Just you have stochasticity, and you have one sample per time step, and then you have an inexact gradient updates. This is an argument from Zrnic and Shao that I'm presenting here, which I liked very much because I think it provides like a beautiful intuition. So the first point is just the natural optimization point. An SGD update is an unbiased estimate of the gradient, because your data point is sampled IID from the distribution. So again, imagine this local optimization problem that you're solving. If epsilon is small, so this is so now we are approximating this gradient. But what does this gradient have to do with like the stability that we care about? So the argument they're making is that you're basically solving. You can see SGD as a method to solve the problem at equilibrium. And the argument they're making is that the gradients are aligned. So at any step, K, the gradient of theta on the current distribution and the gradient of theta on the distribution at stability, they have an angle smaller than 90 degrees. So there is a direction of descent on the stable point, even if you use the gradient from previous distributions. And so using this argument and the same threshold, this epsilon smaller than gamma or beta under the same assumptions. So here's the intuition. So the gradients are aligned. You can choose a step size such that the gradient variance decreases, just the normal variance bound assumption you will need here from SGD. And you get this usual 1OK convergence rate. Which is sort of interesting. I just found this idea interesting to consider it as a method for solving the problem at equilibrium. And you can argue about these steps computed from earlier distributions are reasonable update steps on that problem. And you obtain convergence with SGD. So what we do here, I want to just visualize this here. You collect one sample at every time step. You do an SGD update in exact, and then you deploy, and you will see a new problem. You collect one data point, you deploy, and you see a new problem, and so forth, right? Now, this is often very simple, or deployments can be very costly in performative prediction because it means that you deploy a model, you observe how the distribution responds. So a natural relaxation is that you do multiple steps on the same distribution before you deploy. This is what we call lazy deploy in contrast to greedy deploy. It's just an interesting new dimension to sort of stochastic optimization to decide when to deploy. And I think it's just the method is intuitively, the lazy deploy is like an approximation to retraining. Just sort of approximate the optimal solution on the problem you have if you take sufficient steps, and then you can get close to retraining. The stochastic method is different. And you will have a globally decreasing step size schedule for the greedy deploy and the locally decreasing step size for lazy deploy. I think this is like intuitively very clear. And which one works better? Do you have an idea for like intuition for which one you think works better?
work, there's no wrong answer.
There's no wrong answer. That's good.
Uh,
Yeah, as with everything, it depends, right? It's first, just like here is a toy example to sort of simulate the two algorithms and show how it works. This is a mean estimation problem where the mean depends on your parameter, your estimation, right? It's again a bias. You shift the mean depending on what you predict. And here is the convergence of the two methods for different parameters for epsilon. So further to the right is stronger, more performative, larger sensitivity. And what you can find in these empirical investigations is that greedy deploy is better if performativity is weak. We know that greedy deploy, so SGD, is a good thing to do on a static distribution. Lazy deploy, so the more like local version where you is better to deal with strong shifts and poor initialization. It's just sort of the finding. So even in terms of sample complexity, this is now like x-axis is number of samples. If you look at number of deployments, I mean, lazy deploy can be way more effective. So in this extreme case where we have strong performativity, we can see that it's about 50K deployments for greedy deploy and 200 for lazy deploy. The figure on the right, the point on the very right. So there are a lot of interesting trade-offs here in stochastic optimization once you start thinking about the effect of deployments on distributions. We can go beyond convexity. So there's recent work on stochastic optimization in non-convex settings. Here there's a generalization of stability to like a stationarity condition. So the gradient being 0 on the distribution that you induce. This also makes sense if you have non-convex losses. And there's also more general definition of approximate stationary performative stability. So you assume that the gradient is close to 0. You allow for some slack, so delta here in that definition. And they show that if under the same sensitivity assumption, they have like two different distribution distances they consider. Under different sensitivity assumptions and Lipschitzness of the loss, it's now a Lipschitzness assumption, and possibly non-convex losses, you still get sort of convergence to something that's close to stationary, where you have like a bias in your solution that depends on epsilon. And for greedy deploy, this bias can be reduced by making the batch size larger. Sort of the result different. Yes. Sorry, can you repeat about?
Yeah, I don't know whether you're going to talk about the structure of the equilibrium later or not, but since now we're talking about complexity, I was just wondering whether you know what the equilibrium is unique, or you may have multiple equilibria.
Yeah, so yes, so thank you for giving me the opportunity to talk about. So in the retraining result, in the original one with strong convexity, we have uniqueness of the equilibrium. So there is one equilibrium, and we'll find it with retraining under these assumptions that we have. In a non-convex case, I think this is like unclear. You can have different stable points. I don't think there's any claim here about uniqueness or, yeah.
But it's worth mentioning just that this, so it is true that in this like retraining result, we have a unique equilibrium, but that's not assuming that in there. That's just implied from the assumption. It's just like emerges from there.
From everywhere you converge to that point, so it must be unique existence. So you lose this guarantee here. Yeah, this slide is more meant to show that people have thought about the non-convex case, and then yeah, things get there is an analog, conceptual analog, but the results get much weaker, and it's also unclear where you converge to. Yes. Yeah, so if there's a unique distribution, there's also a unique, if there's a unique equilibrium, there's also a unique distribution that you will find with this procedure. And here, there might be different points, and they might induce very different distributions, right? They are qualitatively very different if you look at it from the perspective of what you cause to people, what sort of the distribution that you induce. Yeah, since there've been a lot of questions about beyond stability, so I think just let's quickly recap what we've seen here. We have seen that stability is a natural equilibrium concept. We've seen that retraining heuristics converge to these stable points if the problem is close to static. So these sort of methods that we are used to deploy still converge to something that's like a performatively stable point. We have talked about online and offline updates as a new design choice in stochastic optimization. So how far do I optimize before I deploy? If I have trade-offs between cost of sampling and cost of deployment. And so next we will talk about different solution concepts in this setting, which I think will maybe answer a couple of questions that came up now. And I'll head over to Tijana for that part.
Also, we can take questions
Sure.
while we're switching. Yeah, I think I'll have to do it. Thank you.
Let's come to that.
Yeah, you guys are anticipating the whole tutorial. That's it's gonna come.
For now, it's sort of important, right? What we've talked about so far was not assuming any model. These results hold independent just under this Lipschitz assumption. We didn't require your knowledge of how the distribution is found. I think that's the important part. Because it's it can be hard to model. We will see a couple of approaches, but yeah, it's tempting to model it. I think it's also maybe sometimes a bit challenging and hard to do. So we'll talk about some of these trade-offs. Yeah, it's a condition under which retraining converges. Yes, it's an assumption. Yes, it's a sort of more.
Can you verify that this is classified in real world data?
Yeah, that's a very good question. I mean, it sounds hard to verify that condition just globally because it's a condition that, for all theta prime. But, probably if you had that condition satisfied like locally where your optimization will actually happen, that's probably sufficient and maybe like more testable somehow. But yeah, I think it's tricky. The short answer is I think it's tricky. Oh, yes, sorry. Yeah, we're supposed to repeat questions. Yeah, sorry. The question was, thank you for the reminder. The question was if we can test the sensitivity assumption in practice. Okay, so if there are no more questions, we'll move on to the next part. So now we'll talk about performative optimality. Okay, so what we saw in the previous part of the talk is that once we deploy model theta, we incur risk that depends on the distribution that will be induced by this deployment of model theta. So we call this risk the performative risk. So that is the risk of model theta on its induced distribution. And so if this is our main measure of performance, then the most natural solution concept that we might want to optimize for is performative optimality. So that's just the minimization of this performative risk objective. And we'll call this point theta PO the performative optimum. So again, this point achieves lowest possible risk after deployment. Okay, but what we talked about previously is a different solution concept. So we talked about performative stability, and you can see that the definitions are, they resemble each other, but they're not exactly the same. So performative stability is defined via this fixed point condition. So it says, once we deploy the stable point, there will be some distribution that is induced. And then if we retrain on that distribution, treating it as just a standard static problem, we're hoping to get the same thing back. So that's not exactly the same as performative optimality. And just a quick remark, in the previous part of the talk, we used theta star to denote stable points. But here we will have these two competing solution concepts. So we'll use these subscripts PO and PS to refer to performative optimality and performative stability, just to be super explicit about which solution we're talking about. Okay, so given that performative stability does not exactly match this definition of performative optimality, and intuitively it feels like performative optimality is what we want, then a natural question is, what can we say about the performative risk of stable points? So do performatively stable points have low risk after deployment? Okay, so again, we said by definition, performative stability says that on your own distribution, you look optimal. So it feels like some kind of local definition of optimality. Okay, so now let's try to understand, just zooming out, what can we say about the performative risk of stable points? Okay, so this is just a definition of performative risk that we had previously, and now I'll just add and subtract a term. So this term that we're adding at subtracting is the best possible risk that you can achieve on the distribution d of theta by using models in your function class. So I didn't do anything, I just added and subtracted the term. But if you think about it, at the stable point, these first two terms add up to 0, because stability by definition says your point is the best possible point on the induced distribution. So what we see as a result is that the performative risk at a stable point will essentially be equal to this best possible risk that we can achieve on that distribution. So intuitively, that's like the easiness of d of theta. So because the performative risk at a stable point corresponds to the easiness of the induced distribution, we can immediately see that stable points will be approximately optimal if they induce easy distributions. And just to quickly sketch this difference between stable points and optimal points. So here, this curve that we're drawing is the risk on the distribution that will be induced by the stable point. And so by definition, the stable point has to be at the minimum of that function. But now, what can happen at performative optimality is you can have a different risk curve that's induced by the performatively optimal point. And the performative optimum is not going to be at the bottom of that curve. It might be somewhere around the bottom, but you can see that because the curve induced by the performative optimum is lower, like dips lower than the curve induced by the stable point, we can still prefer the performative optimum. We can get better performance at the performative optimum, even though this blue point is not at the minimum of the curve. And that's pretty important. And that's also an important distinction to remember about stable points and optimal points. So if we're at a stable point, we can pretty easily verify that we're at a stable point, because we just need to collect data from the induced distribution. We see our gradients are vanishing, everything's good. We know that we're at a stable point. If I give you the optimal point, and I promise you that that's the optimal point, you won't see vanishing gradients necessarily. So it will be harder for you to verify that what I'm promising you is the optimal point is actually the optimal point. And I think that that's pretty interesting. Okay, so the unfortunate thing about stable points is that it's not necessarily going to be true that they induce easy distributions. And in fact, it's not hard to see in very toy examples that stable points can even maximize the performative risk. So they can even give you the worst possible solution. So to illustrate this point, let's look at a very, very simple toy example. So let's say that our features are just uniform between -1 and 1. So they're just Rademakers. And let's say that our label distribution given X is just a biased coin flip, basically. So the mean will be 0.5 plus some bias that will depend on theta. So it will depend on these performative effects. And our loss is just the squared loss, where the predictions that we're using will be, again, 0.5 plus some bias, because we are essentially trying to fit this bias. So in this problem, basically all the assumptions that we talked about previously are satisfied. This is a very regular problem. In particular, we have epsilon sensitivity that we required for retraining, and we also have strong convexity and smoothness. So what this means is that when epsilon is less than 1, when it's less than this gamma over beta threshold, then retraining will converge to a unique stable point. And it's not hard to verify that the stable point in this problem is just equal to 0. But if you do a quick calculation and you compute the performative risk in this problem, so you just compute the expected loss over df theta, you will see that the performative risk is quadratic in theta. But whether it's a convex quadratic or a concave quadratic really depends on where this epsilon is. And in particular, it exhibits a threshold at epsilon equal to 0.5. So what this means is that we can have all the conditions that are necessary for retraining to converge satisfied. So retraining will converge, but it will converge to the worst possible point in a certain regime of epsilons. In particular, when epsilon is between gamma over 2 beta and gamma over beta. So this toy example just means to basically motivate why we need to go beyond retraining if we want to have robust methods that will actually optimize the performative risk in a reliable way. Okay, so we need to basically think about what conditions and what tools we need to optimize the performative risk. I think it's useful to first start from understanding the difficulties of this problem. So the first difficulty is that even in settings where supervised learning works very well, such as if we have convex losses, here the loss, our objective function, the performative risk, need not be convex. And that's very important to remember because our loss being convex only tells us that this risk function is convex in the first argument, but we have an extra dependence on theta through this distribution argument. So this extra dependence on theta could completely break the convexity of our objective, and there's no reason for this PR to be convex. The other difficulty is that we no longer have gradient access. So if we try to just analytically compute the gradient of the performative risk, we'll have a first term that looks a lot like terms that we see in standard supervised learning. So we're fine with the first term. But the problem is that there's an extra term that basically depends on the form of the distribution map. So here we're just assuming that d of theta has a density and we're denoting it by p theta. So we see that we have some nasty looking gradient that depends on knowledge of the distribution map. But we don't know the distribution map, and so we can't compute this second term. And really the fact that the distribution map is unknown is the main obstacle in finding a performative optima. So what we'll need to do across many different settings that we'll talk about is we'll need to have data from multiple deployments of different thetas. We'll need to deploy thetas repeatedly to be able to learn something about the distribution map. And so we'll see that all the methods that we'll talk about in the remainder of the second part will basically follow the same form. So over T sequential rounds, we will deploy a model. We will collect data from the distribution that will be induced by this deployment. And then we will somehow aggregate all this data, these deployments and the data collected into some kind of strategy that will approximate the performative optimum. And we'll see different families of methods for approximating the optimum. Are there any questions? Yes.
How did that develop law? Why are the logarithm of this?
Oh, yeah, it's just, yeah, basically, you're just using the fact that the derivative of the log will be like 1 over x. You basically like multiply and divide by the density of d of theta. Yeah, and then you see that the thing that you get is exactly the gradient of the that it's the
You
log.
just start with the expectation of the gradient, right?
What, sorry?
You start with the.
Yeah. It's totally by definition. Yeah, nothing weird. It's just that you get the gradient of the density and the gradient, yeah. The gradient of the density over the density will just be the gradient of the log density. Any other, yes, in some,
The Western.
yeah, sorry. Okay, I'm really, yeah. Thank you for the reminder. I'm really bad at this. Okay, so the question was just how we got the log in the second term. And I was just saying that it's a completely analytical derivation. If you will get the gradient of the density, and then you just multiply and divide by the density. And yeah, that's how the log appears. Yep.
And may also be changing data.
Sorry, can you repeat that?
How do you deal with other texts that maybe also change data? So we are getting lots of data, right? People deploy with, but there might be other techniques that also give the data. So how do you do?
Yeah, okay, so to repeat the question is, how do we deal with other factors that might change the data distribution beyond just these performative effects that we're capturing through the distribution map? And I think that's an excellent question. So we will talk about, in the extensions part, we will talk about some other factors that impact the evolution of the data distribution. But maybe what you're getting at is something like, there might be other reasons for distribution shift beyond performativity. Like there might be seasonal effects or some kind of exogenous factors that also cause a distribution shift that just can't be explained by this map D of theta. Our model intrinsically assumes that if I deploy theta today and if I deploy it 2 years from now, I will see the same distribution, and that's not necessarily justified. So I think that that's a great point, and I think that that's actually a great open direction to figure out a model where we can incorporate both these endogenous distribution shifts that come from performativity and just standard exogenous distribution shifts, and then maybe treat it more like as an online learning problem where we want to like maybe, yeah, bound regret over time. Yeah, that's a good question. Mhm. It should be gradient log PZ theta. It's the gradient with respect to Z. Sorry, in this first term? Oh, it should just be L. Yeah. Sorry. It's a typo. Yeah. Yeah, so that's a good question. The question is like whether there will be some bias because we're using the data twice, because we're first using the data while we're deploying these different thetas. And then at the end, we're also using all the data to approximate the performative optimum, right? That captures it? So we'll see different models here. I'm definitely hiding a lot of details. A lot of times these thetas will be deployed non-adaptively. So we won't actually use the data during the deployment process, but we'll just use the data at the very end when we approximate the performative optimum, but we'll just explore according to some, the thetas will be sampled from some Gaussian distribution or something like that. So we'll see, it will depend maybe on the particular algorithm that we have in mind. Yeah.
I think it's possible that your data distribution also depends on the parameter. It's possible that you are not picking a model. Usually, rather you are picking your data distributions for model. So instead of having to do it with a fixed model, you're only modifying the data distribution. The data distribution is not optimized. It is possible that you are minimizing your problem risk such that so data distribution becomes the back end of the model. So you don't learn anything. Your model properly.
Yeah, I think that's a very good point. So I don't know if I'll be able to repeat it exactly in your words, but yeah, I can try to rephrase it and you can tell me if I am doing something totally dumb. So I think what you're saying is the fact that we're finding the performative risk is not telling us that we're somehow learning something like deep about our environment, but we might just be inducing like a very somehow like a very degenerate distribution that somehow like fits our training process. And that's why we're at the optimal point, right? Just the distribution could be very degenerate and not very meaningful. And I think that that's a very good point. And again, in a later part, we'll talk a little bit about how we can choose this loss function. I think that the problem that you're referring to, maybe one way to tackle that problem would be by choosing the loss function carefully. But yeah, totally valid point in general. Any other, yes?
Yes, maybe follow up on this last question. Well, the students correct, there is still nothing in the framework to tell us if the group of the shape in your example from the beginning, with a lot of objects going, if we just pushing our predictions to the left, I think poverty relation until we can't be poverty than before, we get perfect performance.
Exactly. Yeah. Yeah, exactly. So to repeat the question is, yeah, there's nothing that we've said so far about the framework that is telling us that we're somehow inducing a good distribution when we're doing this optimization. We might, you know, the optimum might be trivial. I can give like one example of that is kind of like what you said. So like one of the initial examples that we were thinking about when we started thinking about this problem is the example of lending. So we, in the United States, there are a few different algorithmic ways of computing credit scores for people, and a lot of lending decisions are made based on these credit scores. So you have some features that these scores take in, and they spit out whether you're creditworthy or not. And if this score predicts that you are not very creditworthy, you will get a very high interest rate. And then you might be even more likely to default on a loan. You might be even more likely not to pay back because you were given this high interest rate as a function of you being predicted as not creditworthy. And so like one optimal solution in this problem that just achieves perfect predictive accuracy is predict that everyone is uncreditworthy, give everyone infinite interest rate, no one will pay back their loan. Your predictions are perfect. No one was creditworthy, right? And so I think that that's a very important thing to think about. Unfortunately, we won't give like very concrete solutions. We will touch upon some of these questions during the tutorial, but yeah, I think that figuring out ways to formulate this optimization problem so that you are actually inducing a meaningful distribution, I think that that's very important. And that's, yeah, that's kind of like a key open problem in my view. Okay, so these are some of the difficulties. And as we mentioned, we'll have two different families of optimization problems, optimization methods for finding performative optima. One family will be model-free approaches. The other one will be model-based approaches. So just at a very high level to give an overview of what these approaches will satisfy. So these model-free approaches won't incorporate any modeling of the distribution map. And generally, they will be based on zero-th order optimization and bandit algorithms. And convergence will rely on, of course, we need to make some assumptions to guarantee convergence, but these assumptions will be very non-parametric. They will be very general. So the regularity conditions that we'll assume will be things like convexity, smoothness of the distribution shifts, so like the epsilon sensitivity condition we saw, and so on. And generally, these algorithms will have slow convergence, at least slow convergence compared to the model-based approaches. Okay, so the other side is model-based. So these approaches will be based on incorporating explicit models of df theta. So maybe I'm assuming something about how this df theta comes about, what the people in my population are doing for this df theta to arise. These models will often be based on economic principles. For example, we assume that the agents in the population are rational, they are maximizing some utility, and so on. The convergence will, of course, rely on the models being correct, or at least not being too incorrect. And so we'll see how model misspecification enters the equation. And finally, compared to model-free approaches, these model-based approaches will typically have very fast convergence. The only problem is that convergence might be to some suboptimal point if our model is very misspecified. So we'll see more about that in the next few minutes. Okay, and so before we discuss some general optimization results, we just want to give a quick toy example where we compare one model-free approach to one model-based approach, and we'll see what some of the trade-offs are. And basically, the trade-offs that we see in this toy example, they pretty much carry over to all the algorithms that we'll be talking about. So let's say that the learner just wants to solve a simple linear regression. Then one model-free approach could be deploy many different models data according to some strategy. For all of these different data, you will collect data. So that means that you can just average out the loss on these collected samples for every data that you've deployed. So now that gives you an estimate of the performative risk at all of the deployed data. And then a trivial thing that you can do is at the end, you can just say, okay, I'm going to look at all these losses that I computed, and I'm just going to pick the data that led to the lowest loss. Of course, this is not like a good strategy to have in mind, but it's just an example of something that is model-free. So to implement this strategy, we're not making any assumptions about how performativity arises. Okay, the other possibility would be to use modeling. So maybe we know something about our environment. Maybe this model F data is some kind of credit score. And maybe we know that people want to maximize their credit score subject to some kind of cost that they have for manipulating their data. So we can place an assumption that the agents have a utility that is a trade-off between the score and some cost, in this case, like a simple quadratic cost. And there's some extra parameter gamma that basically trades off between utility and cost. So depending on where gamma is, the agents might have more or less budgets to manipulate their features in order to improve their credit score. And also another common assumption in related literature on strategic classification, say, is that agents only manipulate their x's, but their true y's don't change. So if someone is creditworthy, they're creditworthy regardless. If someone is not creditworthy, they're not creditworthy regardless. So it's not like if the firm deploys a different model that the agents will truly become more or less creditworthy, but they just manipulate the data that they report to the firm to appear a certain way. Okay, and so once we place this assumption that this is what the agents are doing, we are basically getting a model for the distribution map. So this is an explicit model that's parameterized by this parameter gamma. And so then one approach that we can take is we can deploy different models and we can fit this parameter gamma, this trade-off parameter from the data that we collected. And now if we have this gamma, we basically know everything because we know the loss function. Now we also know the distribution map. So we can just plug the distribution map into our risk function and we can just solve for the optimum. So this is just one example of a model-free versus a model-based approach. Now, the question is, what is the trade-off between these two? Any guesses as to when one will work better than the other? Yeah, of course. Yeah, exactly. So if the model is correct, of course, like you want to do the model-based thing. It feels a lot more efficient, right? I'm just fitting this like one-dimensional parameter gamma. I'm just fitting one real number. So if the model is correct, the second approach will be better. And then more generally, the more incorrect my model is, the more the trade-off goes in the favor of model-free approaches. And here's one two illustration of this. So let's say that our model is tau misspecified. In particular, in the model that we saw on the previous slide, we assumed that the labels don't change. We said the true label of an individual doesn't change depending on which theta is deployed. But now let's say that somehow these changes in X do actually have some causal effect on Y. So if I change my data, that somehow leads me to be more or less creditworthy as a result. So there is some effect tau if the changes in the features do actually lead to a change in the label. And now we can see what happens for different values of tau in a simple simulated example. So tau equal to 0 means that there is no misspecification in the model that we saw on the previous slide. And so we can see that these model-based approaches that are the blue curve in all the plots, they converge very, very quickly. The only question is, what do they converge to? So in the first example, they will converge to something good. And we can see that there is a pretty significant gap between what the model-based approach will find and what the model-free approach will find. But then as our misspecification grows, we can see that the risk of the model-based approach also grows. And we prefer to use the model-free approach more and more. And another important thing to consider is what kind of budget we have for the number of deployments. So if we have a very, very large budget for the number of deployments, then we might actually prefer to do the model-free approach, because we know that somewhere in the far, far limit, it will actually drop below the model-based approach for any non-zero level of misspecification. But if we have a very tight budget on the number of deployments, then even in a pretty misspecified case, we might still prefer to use the model-based approach because it converges very, very fast. So anyway, this is like the trade-off in this very toy example, but basically across all the more sophisticated methods that we'll talk about, the same trade-off is true. Any questions? Yep. Yeah. Is it what, sorry? It will be true. It depends on the particular. Yes, thank you. The question is, will the model-free approach converge? Will it converge to the true performative optimum? Do we have some assumptions under which that holds, or is that true in an assumption-free way? I would say the method that I showed on the previous slide, where we just explore different thetas and we pick the best one. So if our theta space is compact and we just explore thetas, let's say, even if it's, yeah, I guess if it's compact and we just explore the thetas uniformly, then eventually we'll converge the performative optimum. The methods that we'll talk about, they will be smarter than the method that we saw on the previous slide, and they will rely on some regularity assumptions such as epsilon sensitivity. So yeah, we will have some assumptions, just not the parametric kind of assumptions that that we have in the model-based approaches. Yeah.
How much of these sort of patterns of performance are sort of due to fitting a misspecified model in general versus due to the effect on the model?
Yeah, that's a great question. So the question is, I guess, more generally, if we are seeing, let's say, elevated risk, how much of that can we explain through a misspecification in modeling versus the performative effects that are being caused, right? The what, sorry?
Yeah.
Yeah, so the relative performance between model free and model based. I would say, yeah, in full generality, it would be, yeah, I don't have anything very concrete to say in full generality, how much of this gap would be attributed to misspecification versus the fact that we're in a performative context. I can try to think about it more during the break. Maybe I have something better to say, but right now, yeah, I think it's hard to say something in full generality. Okay, we should. Okay. So in general, the trade-off that we saw on the previous slide, so we can state this far more formally. We can see that the excess risk of this estimated performative optimum, meaning the gap between the performative risk at the estimated point versus the best possible performative risk, will be upper bounded by a combination of a misspecification error and a statistical error. So this misspecification error will be error due to the modeling of the distribution map. And the statistical error will be the error due to having only finite deployments and finite data. So if we have infinitely many deployments and we collect infinite samples, the statistical error will be 0, but we might still suffer a misspecification error. And so what the idea behind model-free approaches is to basically essentially zero out this misspecification error, but pay a price in the statistical error. So the statistical error will often be pretty large. The model-based approaches, on the other hand, often have a pretty small statistical error. So the convergence is often pretty fast. We get nice parametric rates, such as 1 over root t. But then the gamble is really in terms of the misspecification error. Because if we have a lot of domain knowledge, if the true distribution shifts are actually very simple to capture, we might have pretty low misspecification error. But if we don't have enough domain knowledge, or if the true distribution map is very complex, then this misspecification might be large. So it really depends on how good of a model you have. That really determines how large this misspecification of model-based approaches will be. Okay, so first we'll talk about some results in the context of model-free optimization. So I guess one natural question to ask is, when is the performative risk convex? So we know that as soon as we have convexity, even if we don't have gradient access, the problem should be easier. So the question is, when will the performative risk be convex? Because as we saw, just the convexity of the loss does not imply convexity of this objective due to this extra dependence on df theta. Okay, and so that brings me to the first theorem I want to state. So if we have that the loss function is gamma strongly convex and beta smooth, in the same sense as in the result that Celestine showed, and if we have that the distribution map is epsilon Lipschitz, meaning sensitive and sufficiently regular, then the performative risk will be guaranteed to be convex if and only if this epsilon is less than gamma over 2 beta. So all of these conditions are completely analogous to the conditions that we had in the retraining result, modulo this sufficient regularity. Due to time constraints, I'm not going to get into much detail about this sufficient regularity. I'll just give one example of when it's satisfied, and then you can look at the paper for more details. So if we have this location scale family structure, then that will be a sufficiently regular distribution map. So if we can write every sample from df theta as some kind of rescaling and translation of a base sample, then that will be a sufficiently regular distribution map. But there are other examples that don't necessarily follow this structure. And so there's something interesting here happening, because we saw that retraining converged for epsilon less than gamma over 2 beta. Here we get that this threshold is cut in half. And that exactly corresponds to the threshold that we also saw in that counterexample where we got a concave performative risk. We exactly saw that threshold at gamma over 2 beta. Okay, and so now if this condition is satisfied, if we can show that the performative risk is convex, then there are off-the-shelf things that we can use. So we said we don't have gradient access, but luckily there's vast literature on derivative-free convex optimization. And so here I'm stating one example algorithm that's often known as gradient descent without a gradient. So you can see that it pretty much looks like gradient descent. This eta is the step size, delta is another hyperparameter, d is the dimension of your problem. So we can see that it looks like gradient descent, but we're not really plugging in the gradient. Rather, what we're doing is we're taking our iterate, we're sampling a vector uniformly on the sphere, and then we're evaluating the objective function at that point where we perturb our iterate by this uniformly sampled vector. So it's important to note that this is just querying the performative risk. This is not querying the gradient of the performative risk. So this is much more feasible. Okay, and so we can, not we can show, but this is a classical result. So this is known to converge to the optimum at the following grade. So we get a root d and t to the 1 quarter. Sorry? Oh yeah, sorry, that's the sphere, the d-dimensional sphere. Yeah, it's possible. I would, sorry, to repeat the question. The question was, what is this s to the d minus 1? And I said that's just notation for the d-dimensional sphere. And now the question is, can we also do that on some kind of hypercube in d dimensions? Yeah, my guess would be that a similar result could be derived. Just so what is shown for this particular sampling strategy is that this approximation of the gradient has some small bias relative to the true gradient of the performative risk. And so my guess would be that if we have like a different sampling strategy, just our bias might be larger or might just be different. But I'm not familiar with any work that does this, so I can't say anything too confidently. Yeah. And so kind of like a d-dimensional hypercube. Yeah, it's an interesting point, but yeah, I don't know if this literature on derivative-free convex optimization has studied something like that. Okay. Okay, so in the previous slide, we saw that if we can guarantee that our performative risk is convex, then there are standard approaches in the literature that we can use. But now, still, we had this pretty constraining condition on the sensitivity being bounded and so on. Is there something that we can say beyond this convex setting? So can we somehow optimize the performative risk in full generality? So if you think about at a high level, what we are asking for is we're saying we want to solve an optimization problem where we don't have access to gradients. And now we're also removing convexity. So this very much sounds like a bandit problem, like a continuum arm bandit problem. In particular, when I say bandit problem, I mean that at every time step, we pull an arm theta t, meaning we deploy theta t, and we observe a noisy estimate of the performative risk at that deployed point. So there are, again, there's a vast literature out there on how we can optimize under this observation model. Maybe one piece of work that was closest to how we were modeling this problem is this literature on Lipschitz bandits. So if we assume that the performative risk is just Lipschitz, then we can apply these algorithms and we can minimize regret with respect to the performative optimum. But one interesting thing to note is that while it is sufficient to apply Lipschitz bandits, we might actually be able to do something different. And the reason is that the feedback that we are getting is actually richer than just observing this PR hat. And the reason why this feedback is richer, why it's more informative, is because we're actually observing samples from the induced distribution. So we are not just observing an estimate of the performative risk at the deploy point, but we are also observing an estimate of the distribution. So what that means, for example, is that we can evaluate the performance of any model on samples from a particular distribution. Like maybe I've deployed theta, but now I'm wondering about the performance of theta prime on the distribution theta. I can still evaluate that. And it turns out that because we can do that, we can actually get even better algorithms in this context. So in particular, we can get faster convergence rates by constructing finer grained confidence bounds. And so in the next few slides, we'll sketch how we construct these finer grained confidence bounds. Any questions?
You want to trade off number of iterations with number of samples.
Yeah, we're not going to trade off anything. We'll just assume that at every deployment that we're collecting a fixed number of samples. But yeah, just for simplicity, we'll keep the noise constant everywhere. But yeah, probably if you were to do something. Oh no, actually, wait. So sorry. Yeah, the way we model it, we do assume that you're observing the constant number of samples per deployment, but then what we'll do is we'll deploy the model for more and more rounds so that over time we get like finer and finer estimates of the performative risk. So we will actually change the number of samples over time. Now that I think. Okay, so this is roughly the intuition behind these tighter confidence bounds. So again, after deploying theta, let's say that we observe d of theta. So obviously there are finite sample considerations that we have to take care of, but this is just a sketch. Let's say that we actually observe d of theta. So now the question is, what can we say about the performative risk of some point theta nu that we've never deployed? So we've never looked at this point before. Okay, so now we're just adding and subtracting terms. So here we just added and subtracted this risk of point theta nu on the distribution induced by theta t. So we didn't do anything, we just added and subtracted the term. So by doing that, we've basically decomposed this gap between the performative risk at the new point and at the old point into an uncertainty due to the distribution shift and an uncertainty due to changing the predictive model. But now what's interesting is that the second term is known because we know d of theta t. So we actually don't have any uncertainty due to changing the predictive model because we have the distribution d of theta t, so we can just plug it directly into the risk and we can just evaluate what's this second term. So really, we only have to pay for the uncertainty due to the distribution shift. And that is the main difference compared to just standard Lipschitz bandits. Okay, and so to give like a visual illustration of what happens. So let's say that this is our performative risk curve. And let's say that we deployed this point that's denoted on the in the image. Then in standard Lipschitz bandits, obviously we assume that this performative risk is Lipschitz. Then our uncertainty about the risk of any other point just linearly grows as we move away from the point that we've deployed, because things can just shift proportionally to the distance to the point that we've deployed. Okay, so then if I'm wondering about this point theta nu, then I know that its risk is somewhere in this interval that's denoted in orange. So we know that it's somewhere in that band. Now, what we can do with this performative feedback, if we incorporate this error decomposition that we saw on the previous slide, so where we only pay for the uncertainty due to the distribution shift, our confidence bands don't have to grow linearly as we move away from the point that we've deployed, but they can actually track the shape of the performative risk much more closely. And in particular, for the same point theta nu, we can get a much tighter confidence band for where its risk lies. And now what I think is particularly interesting about this second feedback model is that, so if we look at this point theta nu, we can see that the upper limit of this confidence band, meaning the worst possible risk that we can have at that point, is better than the best possible risk we can have at some other points. In particular, in these shaded regions, the best possible risk that we could have in the shaded region is worse than the worst possible risk that we can have at theta nu. So that means that we can just automatically discard these parts of the parameter space without ever having deployed a single point in that part of the parameter space. And that's because of this richer feedback structure and this error decomposition that we saw on the previous slide. Okay, and so now, of course, here we explained everything, just assuming that we observe full distributions. Of course, in practice, that's not going to be the case. The way that we handle finite sample uncertainty is by using successive elimination, which is a standard bandit algorithm. Okay, and so in particular, this is what the main theorem says. So again, under the same epsilon sensitivity assumption on the distribution map, if we also assume that the loss is Lipschitz in the Z argument, then this performative confidence bounds algorithm that we sketched will have this regret rate right here after T deployments. So we see that we have two terms. We see that we definitely have to suffer the root T regret. The second term has this bad exponential dependence on D, but the good thing is that it's multiplied by something that depends on epsilon. So in particular, if the distribution shifts are very, very weak, then we don't have to suffer from the second term as much. It's probably most useful to compare and contrast that rate with the just standard Lipschitz bandit rate that we would have gotten had we just assumed that the performative risk is Lipschitz. So we can see a pretty similar rate, but this D in the top theorem and D in the Lipschitz bandits is not the same D. So this D prime is also some kind of zooming dimension. Both are a zooming dimension, which I'm happy to talk more offline about what the zooming dimension is. It's a notion of dimensionality that depends kind of on the curvature of your problem. So if your minimum is very, very obvious, then the zooming dimension will be small. And in the very worst case, the zooming dimension will just be the dimension of the whole parameter space. So this zooming dimension in the Lipschitz bandits result will be no smaller than the zooming dimension in the result under performativity. Okay, and so just to again quickly go over the benefits of the performative confidence bounds algorithm. So we see that the regret bound scales with epsilon. In particular, if we don't have any distribution shift, then we will get a fast root T rate. As epsilon, so yeah, that's what I just said. So if we let epsilon tend to 0, then we'll just get root T. In particular, we won't get any dimension dependence. And finally, we don't have to make any assumption on the loss as a function of theta. So when we use Lipschitz bandits, we have to assume that the whole performative risk is Lipschitz in theta. But if we're using this performative feedback, we don't have to assume anything about how L depends on theta. It can be, it can have like a perfectly irregular shape. Okay, so that's, yeah. What, sorry? Oh, the regret definition is, that's the definition, sorry. The middle term, the question is, what is the regret definition? And I'm saying the definition of regret is exactly this term in the middle. So it's just the cumulative difference between the performative risk at the deployed points and the true performative risk. So we add up the gaps between the induced performative risk and the best possible performative risk. Yeah. So it's, yeah, analogous to, I guess, standard notions of threat. Any other questions before we get to the model-based part? Yes.
So it's like you were thinking that sometimes using the output is probably to the better people. So I have two questions. One, can one people something like an active learning speed to and two, how can we ensure the exploration?
Okay, so the question is, yeah, let me maybe answer the first question and then, yeah, I'm not sure if I understood the second one. So the first question is, yeah, can we, okay, we're using like a particular upper confidence bound like algorithm. Can we use some kind of active learning to make improvements? It's possible that I don't know exactly what you mean when you say active learning. I think of active learning as usually being like, I am adaptively choosing my data points to learn some like, you know, labeling function or something like that to like learn where a decision boundary is. And yeah, I'm not exactly sure what that would mean here. I would say like one question that is maybe related to what you're saying is like, why couldn't we use like the UCB, like some other bandit algorithm? There are, yeah, the short answer is somehow like the proof doesn't quite work out with a different, it's like very particularly tailored to this successive elimination strategy. So yeah, I'm not really sure that this is the kind of argument that you can just combine with any standard bandit argument, you know, or active learning or something like that. So yeah, I think the answer is kind of like, I think it doesn't exactly combine well with any bandit argument. And yeah.
So I was thinking about we are trying to learn depending on that depending on the team, right?
Mhm.
To learn this maybe more efficiently, maybe we can use because such that they are more informative and we learn this like with less than we
I see. Okay. Okay. So now I understand. Okay. So the question is, yeah, can we somehow use active learning to learn d of theta better? Can we somehow like strategically pick thetas so we learn d of theta better? I would say that is implicitly part of the algorithm. Like the thetas that are being sampled are sampled very strategically where you have the highest uncertainty about your d of theta. So that is implicitly happening, and we'll see that there is some analog of that also in the context of model-based approaches. When you're trying to learn a model, you should also pick the thetas so that they help you most in learning your model. Yeah, it's a good question.
Important here, right? We're exploring where there is high uncertainty, so also where the distribution could shift, but we're not learning the distribution. We're just finding optimizer. So the result we have, do not allow us to sort of extrapolate to other loss functions. We just know what's the minimum of that objective. But we'll get to the model-based part now.
Yeah, exactly. So yeah, we're not exactly like learning d of theta in the sense that at the end of the day, we don't have like d of theta as, you know, like a product of the algorithm. But yeah, we are intuitively, yeah, we are sampling where the uncertainty about d is high, as demonstrated by the performative risk. Okay, yeah. 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 Yeah, it's because I know exactly the shape of the loss. Like I know exactly the shape of the loss function. If I go from one point to another point, I know what the value of like L theta is at that point. I just don't know exactly like how much the sensitivity changed the distribution, but I still know this like general shape of the loss. And that's why the bounds end up tracking the shape of the loss. Yeah. Yeah, sorry, the question was giving more intuition behind this picture. Okay, so maybe just in the interest of time, I'll move on to the model-based part. Okay, so yeah, in model-based approaches, the basic idea is to try to learn a model of the distribution map and then plug it into the performative risk. So let's denote by d hat of theta, this fitted model of the distribution map based on all the data that we've collected. Then what we can do is we can just plug in this model that we've learned into the performative risk objective, and we can just solve for the minimum. So now in this risk objective, all the terms are known. We should just be able to solve for theta. And related to the point also that Celestine just made, this is a pretty powerful approach if you think about it, because if we are able to identify this d of theta correctly, then that actually allows us to do a lot more things. In particular, we can even change the loss function and find the optimal solution offline. And I'll just mention, in case people are maybe familiar with this literature, this is pretty related to the concept of omni-prediction. So doing these model-based approaches also gives us a model of the distribution map, and that's a lot more powerful. Okay, so one common way in the literature that people use to model the distribution map is by using so-called microfoundations. So microfoundations is a term that comes from economics, and it refers to the idea that we can model macro level phenomena using micro level assumptions. In particular here, we can model this distribution map, which is essentially a macro level phenomenon. It's just like the data that comes as an aggregate to us as a learner. We can get at that data by modeling what the individual agents in the population are doing. And so one literature that frequently makes use of these microfoundations is strategic classification, where the assumption is that this distribution d of theta comes from strategic behavior of individuals that are trying to adapt to a decision rule. So this is often the setup. So we have some decision rule. To the right of the decision rule, we're going to classify people as positive. To the left of the decision rule, we're going to classify people as negative. And the assumption is that everyone wants to be classified as positive. So this might be some kind of allocation of a benefit or something similar. And the model that is often used in this literature is the model that we saw a few slides ago, but maybe this is a more general formulation. So the model assumes some kind of trade-off between utility and cost. So the agents want to have the highest possible prediction, but subject to some cost. So they can't manipulate their features arbitrarily, but they have to suffer some cost for manipulating their features. So if we satisfy this assumption, so if all the agents really act according to this model, then they are basically forming on aggregate a distribution map that's parameterized by whatever is unknown about this model. So often only a gamma will be modeled as unknown. Sometimes also the cost will be modeled as unknown. So in either case, we're getting some family of distribution maps that are parameterized by whatever is unknown in the equation. Okay, and so this is how the agents move. So if we say that this prediction is just 0, 1, so it's just a binary prediction, then only the agents that are close enough to the decision boundary will move and try to cross the decision boundary. So this might be our d of theta. So after the agents have moved to the decision boundary. Okay, so in conclusion, the way we can think about strategic classification is it's essentially an instance of performative prediction where we additionally apply a microfoundation model to model these distribution shifts. So it's a combination of performative prediction and microfoundations. Okay, so this is an example of a micro level model. We can also go to macro level modeling. So this is one model that's been looked at in the literature. It's essentially a location family. So we're assuming that d of theta is essentially a fixed distribution shifted by some linear function of theta. Okay, and that is, this macro level model is actually implied by the strategic classification model that we saw on the previous slide, if this utility is linear and the cost is a quadratic. And so that's not hard to just analytically verify. Okay, and so for this location family model, we can get the following regret rate. So we get something that's root t and essentially linear in the dimension of the problem. And it's interesting to contrast this rate with the bandit rate. So in the bandit case, we got a much worse dependence on the dimension. The only way we could kill this exponential dependence on the dimension is if our performative effects are very, very weak. Here, when we assume the location family structure, we are basically getting a fast rate regardless of the strength of performative effects, because we have this very explicit and simple model. Yeah.
The key point factor to the theta is the F and also the shape. It's the same theta.
It's the same theta. Yes, it's the same theta. So here we're trying to model basically like, we know that in d of theta that there will be some dependence on theta, and we're just assuming that it's a very simple dependence on theta. Yeah, and the reason why it's linear, why this model implies a linear shift, yeah, is exactly because f is linear in theta. Yeah, and
I could have a nonlinear on that.
sorry, this is the whole model. So this is the model. I'm just saying that this implies that. Yeah. So if this is something very nonlinear, it's not going to imply this. But this is, yeah, so this is not an assumption in this result that we stated. This is the only assumption. I'm just giving the right-hand side as an example of something that will imply the model. Yeah, sorry if I'm being a little bit fast and just trying to, yeah, meet the time. Okay, and so just the last point that I want to make in this model-based part is that essentially modeling the distribution map is fundamentally a causal inference problem, because this d of theta is exactly the effect of deploying a particular model theta. So learning the distribution map is really analogous to causal identification that we talk about in the context of causal inference. Now, of course, we can't do any identification if we also don't have some amount of exploration. So if our predictive model is just fixed, we can't say anything. So Celestine gave this example of the Zillow algorithm. So if Zillow just has a fixed pricing algorithm that it never changes, then we can't tell the difference between, an environment that just doesn't respond at all to the presence of Zillow and an environment where Zillow has like a very strong performative effect. We need to be able to play around with different theta to see, to basically identify the effect of Zillow on its environment. So if we look at the causal literature, we know that if we randomize theta, that will allow identification. And so here I want to just mention some works that look at this special model that's actually very ubiquitous in these applications where we encounter performativity. And that is the setting where the performative effects are mediated by model predictions. So often the only way that a model actually has an effect on its environment is through the predictions that it's making. So the only dependence on theta is through the predictions f theta of x. And this is one example causal graph where that arises. So we make these predictions, and then these predictions can impact our outcome y that we're trying to predict. Now, of course, if we can identify all the functional relationships in this causal graph, then we can just solve for performative optima. But that is not easy. And the main reason why it's not easy in practice is that this positivity assumption is violated. So f theta of x, again, as we said on the previous slide, it's often deterministic. If we just have deterministic predictions, we can't say anything. We can't attribute any effect to the prediction versus, maybe statically, that's just how the relationships are. So I'll just mention this work from Celestine and colleagues where they identify different conditions that enable identification. In particular, they show that if you randomize predictions, of course, that enables identification, but they also find some other conditions that are not that hard to satisfy in a prediction context, but they will still allow identification. In particular, if we're in an overparameterized regime or if the predictions are somehow discretized, that all allows identification. And I invite you to look at the paper for more details. Okay, so here they run a semi-synthetic experiment on a US census data. So I think it's interesting to see this example because we can see that even if we somehow have the right intuition of, we want to take into account our performative effects when optimizing the performative risk, that can actually maybe even be a bad idea. So in particular, if our model is deterministic, and if we include the model predictions as a feature, so we know that our model predictions have an effect on the outcome that we're trying to predict. So it's a natural thing to think like, okay, let's just include these model predictions as a feature in our model. So we can see that if we do that, then that can actually blow up our performative risk. So that's not necessarily the right thing to do. And then in the second and third panel, you can see that if these assumptions for identification are satisfied, then using the prediction as a feature is in fact a good idea. So if we have randomized predictions or if the predictions are discretized, then we can get much better performative risk by taking into account the performativity through these predictions. Okay, so just to give a quick recap of this second part of the tutorial. So we started by talking about performative stability, and we saw that performative stability can in fact be pretty far from performatively optimal. We saw that finding performative optima requires exploring different models. We saw two different families of approaches to performative optimization, model-based and model-free. We said that model-free approaches make fewer assumptions, but they also converge more slowly than model-based approaches. Model-based approaches, on the other hand, usually will make strong modeling assumptions, but the benefit is that we get very fast convergence. And yeah, next up is the coffee break, and we'll be around, so we're happy to take questions. Thank you.
If you work on what's coming.
try to speaking because I'll be, you'll mostly.
Hello, test, test. Oh, now I can actually hear something.
Yeah, now it's better.
we should, is it good? Yeah, sorry. Okay, yeah, so so as I was saying, one extension that's received a lot of attention is this extension to stateful distribution shifts. So it makes sense that if we deploy a model theta, that our environment doesn't just instantaneously move to a new distribution d of theta, but it might gradually gradually equilibrate this distribution d of theta. So in this particular extension, the model is that the distribution that we're observing remembers past deployments and only gradually moves to this d of theta. So there are a few different competing models. There are a few different competing models for these stateful distribution shifts. Here, I will just show one. So we're assuming that the distribution at time t is a mixture between the distribution observed at the previous time step. Maybe let's.
Okay.
That it just stopped. Okay, thanks. Okay, yeah, so we're assuming that the distribution at time t is a convex combination between the distribution at time t minus 1 and the distribution d of the deployed model. So we're gradually moving towards the distribution that's induced by the deployed model. Now, yeah, okay, so this parameter delta basically tunes how fast the environment forgets past deployments. And this theta t is the model that's deployed at time t. And then, of course, like we can see that if we deploy the same model multiple times, if we deploy a model over multiple time steps, then our distribution will get closer and closer to this distribution d of theta, and we will basically be back to the original framework that we saw. Okay, so visually, if you want to think about what this looks like, let's say that at time t minus 1, we're this distribution dt minus 1, then we deploy theta t. We're not going to move all the way to this distribution d of theta t, but we will move in that direction. So then maybe this is our distribution at time t. Then again, we pick the point to deploy at time t plus 1. We're not going to move all the way to that point, but we're just going to move in that direction. And so these works that are listed in the top right, will share all the references after the tutorial. They give different optimization algorithms for finding both stable and optimal points under this formalism. Another extension that's quite interesting is the extension to multiplayer performative prediction. So here the assumption is that performativity arises in the context of n competing decision makers. And the risk of any one decision maker depends on everyone's decisions. So if you want to keep an example in mind, you can think about there being multiple navigation apps. Maybe there's Google Maps, there's Apple Maps, there's Waze, and so on. And when people are deciding on routing decisions, they have all of these different competing apps at their disposal. So the final environment that we're observing is a result of responses to all of these existing models that we can choose from. And so the risk of decision maker I depends on everyone else's models. So the risk that Google Maps incurs depends on what Apple is deploying, what Waze is deploying, and so on. And so the main solution concept that is studied in this line of work is the Nash equilibrium between these players. And so again, you can see something interesting here because we are still requiring this kind of like performative optimality condition, but now we also have this kind of like equilibrium between different players. And so this gets quite a bit more complex. Okay, and finally, I just want to bring up some connections to fairness because there are a lot of works that are pretty relevant to ours that even predate the first performative prediction paper. So one question in the context of fairness is how do we choose this loss L? So I think that there have been several questions during the first part of the talk that are about how do we ensure that we're not converging to some very degenerate solution where the distribution is degenerate. So because of course in these performative contexts, this loss L shouldn't just measure predictive accuracy. It has to incorporate some amount of, a notion of welfare, because we are also changing the distribution in our environment. Prior works that also predate performative prediction have observed that if we neglect this performative feedback, and if we just set the loss to be a standard supervised learning loss, then if we do this performative optimization, that can, or rather, if we do this repeated retraining, we can amplify unfairness and polarization over time, even if we start initially from a fair place. And what's interesting is that this welfare can be captured in the definition of the performative risk through this dependence on DF data. So for example, we can choose our loss function to have an extra regularizer that only depends on the data. So that looks kind of nonsensical coming from a standard optimization perspective, because if we want to take gradients with respect to theta of this objective, that will just kill the second term. So that doesn't seem to make sense. But if you think about it, the distribution of y will depend on theta through the dependence on d of theta. So we can, in fact, add regularizers that only depend on the data point. And that's pretty interesting. In fact, the loss can even depend only on the data. So for example, a valid loss is just to say the loss is equal to y, because the performative risk of this loss is just the expectation of y according to d of theta. So we can still optimize, by choosing d of theta, we can still optimize this loss. And so I think finding strategies for picking these losses in some informed way to optimize a notion of welfare is a largely unexplored but super interesting direction. Yeah, and with that, we'll move on to the last part. Yeah, maybe if there are some questions, we can take a very quick one.
No question. Good. Good or bad or cool. Yeah. So we would like to dedicate this last part to a bit of a shift in perspective. We've talked a lot about optimization and the performative risk as an objective and how do we find solutions. And we want to put this a bit more in a broader perspective. So yeah, we've seen this a couple of times now. So there's the performative risk, which depends on a model in two ways, through the data and through the model. The loss, we often talked about objective of the firm, can be an accuracy objective, can also be a utility objective, whatever they care about. Tijana mentioned just before that they might hope, we hope they incorporate some sort of fairness into that objective, but it's actually the objective of the firm, those that optimize the models. So there are two ways here to be good at minimizing the performative risk, which I think is a nice takeaway from performative prediction. So there's this way to be good at minimizing risk through steering. So you fit the data to conform your predictions to allow for whatever small loss in the problem, or you fit patterns in data. There are two ways. And if you just naively optimize the performative risk through experiments, A/B tests, you're implicitly doing both these levers. In retraining, we were just focusing on learning. We just focused on fitting patterns, but then we still deployed, right? We just didn't explicitly optimize for the second one, but there's still some steering going on. I think that's like an important conceptual takeaway from the performative risks, that there are two ways to be good at prediction. And so this notion of steering is interesting because it's a major concern for digital market regulation. So in antitrust, there was this famous case of the EU Commission against Alphabet Inc., so the firm behind Google, that has been running from 2010 until 2017. It's a really huge case, and they were found guilty with a fine of over $2 billion. So this is one of the biggest antitrust cases that have been run in history. And the central claim of the case is that Google was found to favor its own comparison shopping services on the general search page by means of a ranking algorithm. And they departed from competition on the merits. So by the way they arranged results on Google search, they were favoring their own. So a comparison shopping service is like a platform like where you can compare products, like Amazon is also one of them. So you can, they offer that themselves, Google, and they were favoring their own product in the ranking. And because they did that, they were distorting traffic in the downstream market. So these kind of predictions about what you want to see after you enter a query on search, the way they were displayed were like found to be anti-competitive. So what we see here is that traditionally market power has enabled firms to set prices. That's the standard econ model that we've been working with for a long time. But now in the digital markets, power has like an additional dimension, and it enables firms to steer users and drive consumptions. And I think this is a lot about performativity here. So this link is coming from performativity now. With that in mind, I want to discuss a notion of power that's related to what we've seen before. It's about the strength of performativity. So power as the ability to steer users. So the proposition, the definition here is the following. It's you fix a set of actions that the firm can take, you fit an outcome variable and a population of users, and then you define power as the maximum effect. So the maximum of actions they could take, the average effect on the population on this outcome you care about. So C is the outcome variable, CF0 is the outcome under the base case, just a current an algorithm being deployed, a ranking platform on Google, a ranking algorithm on Google. CF is the counterfactual. If you were to deploy a different model, what would be the effect, the distance in the outcome C in expectation across the population? So that's sort of some notion of power, and it's if you look at it, it's like an average treatment effect. So it's a causal notion. So this concept of coming from performativity allows us to relate this notion about power to a causal inference problem. We specify actions, we specify outcomes we care about, and we go and measure them. I think this is a very interesting notion of power. You can also formalize its role in prediction. So if power is 0, then solutions, performative optima are the same than like supervised learning solutions. The more power you have, the further apart certain solution concepts are. There's like a nice, it plays a role also in optimization. But what I want to focus on is measuring this strength of performativity. If you want to, in a digital marketing investigation, you care about how strong these effects are. I mentioned it's a causal inference problem. So we care about how much would the average outcome change if the firm were to deploy a different model. Here, let's say outcome could be clicks. In the Google Shopping case, you care about incoming traffic to downstream websites, so that's clicks on Google search. The mechanism behind performativity, sort of how people choose what they click after seeing a ranking, can be super complex. There are a lot of behavioral biases playing in. There are many design choices of how you display predictions that impact behavior. So there's also a lot of research on that, sort of position bias in rankings. So it's a complex mechanism. We don't want to model it in that case. So experiments offer a promising avenue to get insights into this measure. So let me just set up a bit of formalism. So how do we measure performative power if we don't have control over the algorithm, right? We're not like the firm deploying the algorithm in general as a researcher or as a regulator. We want to understand that from the outside. And one interesting thing that we can take advantage of is that predictions are often displayed through content arrangements. So you have the prediction, then you have the website that it's exposed to the user, and then the user who makes the decision based on it. So For example, you have a search query, you have a ranking algorithm, and then you have an arrangement here, just illustrated. You decide where to place which element on the website, how large it is, how small it is, how you rank them. So we define the performativity gap as the difference in click-through rate of item I on the two different counterfactual arrangements. So if I were to choose a different arrangement, how much would it change the clicks that item I get? It's this like performativity gap definition. And if we make independent assumptions across interactions, across search queries and user behavior, then performative power across the population of platform users can be lower bounded by the performativity gap, where these arrangements correspond to arrangements that result from algorithmic updates. It can be a subset of them. It can usually we care about small updates that we consider reasonable, some sort of reordering, just small updates is what we care about. And this sort of fact that predictions are mediated by arrangement when they determine outcomes is what we can use in experimental designs. So there has been work, very influential work in applied causal inference, where they use this sort of display to get at this effect of algorithms. Here are two examples. For example, Anderson Magruder, 2012, they had an interesting study on Yelp where they used the regression discontinuity design to get at the effect of a half-star rating. So if your rating is displayed with like 3 stars or 3.5 stars, what's the effect? Even if you have the same score, right? There's the scores are thresholded, and around the threshold, you have items that are basically the same value, but they're displayed differently. And with the regression discontinuity design, you can get at this effect. The interaction, so whether they are based on the assumption that the interactions are independent. Yes. Yes, exactly. No, they don't have this assumption. This is just an assumption about how much do people click a restaurant if it has 3-star versus 3.5 stars if it has the same value. These are just experimental insights. You need the independence assumption to extrapolate the claim to a population or to extrapolate it to a claim about power. If you go from micro-level experiments or insights to a claim about a population, you need these sort of assumptions. So it's more, we need it for relating these claims like this that you get from experiments to a notion of power. That's where the assumption comes in. And the second example here is also a regression discontinuity example on Google Ads, just about how the ranking impacts click-through rate.
So what you're saying, this typically looks like a normal advertising where people take facts in advertising. This is saying, so I mean, we are always saying advertising is it not?
I'm not sure I understand the question correctly. So you're saying that it's natural that you have these effects in.
So it's actually changing some ranks, and that is actually I mean that's a power, and that is actually creating some kind of difference in the revenue generated by someone. If we just talk about normal scenario, not digital scenario, advertising for a firm.
Oh yeah. Okay, so the point is that advertising is also steering consumption, even if it's in a non-digital setting. Is that sort of what you're referring to? Maybe we need to take that offline. I'm not sure I understood your question correctly. I mean, I think these position biases are everywhere. It's just a different scale that we operate at now with like these large scale predictions and personalized predictions. I'm also not like per se, this is just something Google also doesn't like that because it's very hard to extract preferences from the data you get back because it's very much confounded by your algorithm. So these effects is not, they are there and it depends a bit. If you really, in this case, there was a very clear favoring of their own product. So they really took advantage of that effect to distort competition, which was the problem of the case. the fact that it's there, there's nothing you can do about it. It's just if you're an influential company and you have a good service like Google, people use it, and you will have impact on what people consume. I think this is unavoidable.
These sessions is an ad and it works. You'd be like, oh, of course, it's an ad, it works. But we're saying it's some kind of like expression of user preference, right? We're sort of asserting that this is an outcome of something that's not just like, basically we're saying we're not like steer it. Like if we said it's an ad to steer behavior, that was fine. But because we're saying we're not using steer behavior, but it's actually steer, is that like, oh, we can all play that.
Yeah, I'm not completely. So the ad thing is very interesting, right? The whole ad ecosystem is based on performativity. You pay for being ranked top. Why do you pay for being ranked top? Because you know that you're clicked more often if you're in the first position. So it's based on these effects, and it's like, yeah, it's just the position bias thing, the effect of ranking. I think it's everywhere, and it's performativity sort of it's an instance of performativity. That's what I want to say. You have an action and it impacts people. You make predictions about what people want to see, what they like, and it impacts consumption, what they click, and your future data that you collect and that you optimize your models on. But this here is more about, it's really about the impact of algorithms on populations, the impact of ranking on consumption. So maybe we can come back to that. Let me just, I just want to give you some insights because I think there are really nice connections here to causal inference. And from looking at the program, it feels that there are a lot of people at the conference who have worked with these tools. So thought it could be nice to give some insight here. So what I want to say is these numbers speak to the performative power of platforms over participants. But performativity is also very content specific. So the way ranking impacts consumption is not a thing you can say without talking about who is making the predictions in what context. You can predict the traffic pattern prediction. You can predict traffic and be Google releasing them or be someone else releasing them, and the effect would be very different. It's just like very subtle and important in which context you show these predictions and in which make them and how you show them. And I just want to go through a quick case study that's related to the Google Shopping case, where we actually measure that in the context of Google search. So what is the causal effect of Google's ranking algorithm on clicks? Again, algorithm is proprietary. Okay, so yeah, let's say that first. So the algorithm is proprietary. We can't do experiments, but it's nice that these predictions are mediated by display, so we can intervene at the level of display. And so there's it's actually work that I was heavily involved in. So we implemented a browser extension to sort of do this randomization at the level of display to get at these performative effects of ranking. And it's also a bit about how Google was showing their service as featured elements on top versus others in the ranking, and then it was downranking others. It was this combination of adding featured things on top and downranking competitors in this general search results. That was the conduct that was subject of the case. And we wanted to get a bit more insights into this specific conduct in that specific context of Google search. So the extension can hide these like visual elements, and you can downrank and uprank content items.
So my plan is that the extension will participate in it.
Yes, so you would use it because you're excited about this research project and you want to allow academics insights into the causal effect of these algorithms on consumption without relying, because this data is not released, right? From the outside, I want to demo how easy it is to do these experiments, and then you get very, very cool insights and cool data to work with. So the participants of the study, so we had like 85 users over the course of 3 months, 70,000 search queries. It was mostly, people from the academic environment, academic circles, people from like friends. Just it's a mixed group of people. Not claiming about representativeness of anything, but I mean, I'm pretty certain that the findings here are robust. It's just like the effects are just so strong. So the purpose here is to show some of these effects and how easy you can get at them with experiments. So this browser extension runs in the background. Whenever you use Google search, whenever you enter a query, it decides which experimental group you're in, and it either shows it in the default order, or it implements some of these counterfactuals at the query level. You don't see it, there are no glitches, nothing, it's just immediate. And then whenever you click an item, it records the index of the clicked element. So I index elements by 1, 2, 3, 4, 5 in the search results. When you click, I record which one you clicked and which control group you were in, and a couple of configurations of the website. So this is the result when you swap 1 and 2. Not surprising, but still like a huge, enormous effect. So the click-through rate decreased by 44% of the first item on search if you do the change. And then if you swap 1 and 3, again, not so surprising. 3, of course, gets more clicks. 1 gets even fewer, and the second result gets also more. So the fact that the second result, so there are like a couple of indications here in the results that among the counterfactuals we looked at, the Google search ranking is the best one reflecting preferences. Because the first item shown first gets most clicks compared to other items being shown first. And swapping 1 and 3 gets more clicks for 2, indicating that if you assume they go through results in order, indicating that the first one was more relevant than the third one, because more people skip the third one than skip the first one. So there's interesting insights we can get from these experiments, and it sort of says that the power of Google search over incoming traffic to a website in the first position corresponds to more than 44% of base traffic. So this is something that regulators can work with. It gives you a number, you can relate it to something, it's something you measured in the context you care about. There are much less arguments you need to make when stick together like evidence, if you go and actually do the experiments you care about. Just for completion, I mean, we talked about these hiding boxes and swapping results. You can also look at just subsets of queries, for example, where boxes are naturally present. Of course, the confidence sets are a bit larger because it's fewer clicks. If you show the content on top, so in the base rate, we hide the content, then we show it. You can show that they absorb, again, more than 40% of the clicks. And if in addition to showing the content, you also downrank the first result, you compromise like 66% of the click-through rate. For an average result in first position. So it's kind of this experiment shows that the conduct adds up to a larger effect. Hiding and downranking together gives a larger effect.
This effect is so big, I don't think that your assumption.
That's a great point. Haven't thought about that. Do you have any thoughts on that? It depends a bit what you define. So here, definitely there's a discontinuity. Let's say your prediction is like a probability that people click, and then you show it as discrete. At some point, you flip the ranking, right? It's like a discrete decision. And then you have discontinuities, which is a bit of a problem for the sensitivity in any case.
Have these probabilities, and then you sample if you rank the items.
Yeah, if it's a randomized rank, if your ranking is like not deterministic, then you sample based on probabilities, then it might be balance off. Yeah, that's a great point. I think some of these rankings are non-deterministic. Yeah, I'm also not. I don't think it applies. I would also not recommend Google to do retraining. Naive retraining. I'm not seeing this assumption is not an assumption. We're not proposing a method. We're not proposing to do retraining, and assumption is and sensitivity is needed for it to work. We just provide natural conditions under which the thing that we always do, the naive thing, just treating it as a distribution shift, converges. It's more of a descriptive result. But I agree that discontinuities, as you see them often around thresholds, are an issue for sensitivity. Yes. And in fact, many rankings are stable. a lot of rankings will be self-fulfilling. So all these rankings that we had here, that's an interesting point. So all these rankings that we had here, the result showed first got most clicks, and the result second got second most clicks. So at hindsight, if you look at the performance on the distribution that they induce, it looks like they were accurate. They're all stable. So there's definitely not a unique stable point here.
But yeah, I'm also not convinced that like this is not like epsilon sensitive according to some definition, because here like you're swapping things pretty, you're not like perturbing the model slightly, like these are like pretty aggressive.
That's the way you put it, right? We're perturbing the scores slightly such that two adjacent results are swapped. I think it could be a pretty small change to sort of the scores, but it's definitely a very interesting question. I haven't thought about sensitivity in that context. Yeah, there's also power and sensitivity are also very related. So if power is large, sensitivity is large. I know. So yeah, but that's an interesting question. Cool. Yeah, that's just to draw back to this. We had, I don't know, I didn't go into detail, but on the first slide, when motivating performativity, there was this book by Donald McKenzie about an engine, not a camera in financial markets. I really like this analogy. That's why I brought it up here again. He's talking about predictions as an engine that transforms things and not just the camera passively recording the environment. I really like this like metaphor, and I think it also applies to the search engines. Yeah, so this concept of performativity and the notion of performative power has applications in antitrust, as I was trying to illustrate with the Google Shopping case. So in that case, what you really care about is the influence on consumers in a downstream market and how much you can steer what they buy and click. What's interesting from looking at it from that perspective is that you can mandate remedies and then assess their effectiveness by measuring power pre-post. So experiments are just like very useful here. I really think causal inference is very useful here, and the concept of performativity and performative power gives you a way to link the questions they study with the tools that we know a lot about. In consumer protection and fairness, you would, for example, care about certain subgroups and the power over subgroups, how different people are affected differently. Yeah, you can instantiate the definition flexibly. So I think it's like a very general framework that I found useful to think about these things.
Clarification question. So how is the first rule applied? We want to know if a firm has actions at its disposal that have particular effects on consumers. How is this? In my head, this sounds like effect estimation. Effect estimation of their actions that the firm has. And I'm used to the link to performative power. So this is applies to every action that is also not.
Yes, no, I completely agree. It's a treatment effect. It's a specific treatment effect where you assume the action is like an algorithmic action chosen by a predictive model. Yes, it's not, the technical thing is an average treatment effect that you instantiate in the performativity setting. But I think yes, it's just the claim at the heart of the case is a causal argument. And the fact that performative power, this causal argument, is relevant for optimization, prediction. It plays an important role in prediction. The ability to steer this causal effect that we call performative power is relevant for prediction. If we know that performativity is part of like an optimization problem, of a prediction problem, there's suddenly, you can't just talk about prediction without talking about power. It's just like a bit of, it's more sort of, that's the endeavor. But let me go through a second part, and then we can open for a more broader discussion and maybe go through some of these things. Yeah, I want to zoom out a bit more to again talk about performativity. So performativity is the effect of a model or a prediction on a population. We talked about that. And we said that if these predictions are data-driven. The data and the effect feeds back into the model through data. So we have this loop. And we talked about finding performative optima as anticipating this loop, the shifts in the data that you cause to your prediction. But now we could also turn this around, right? There's this loop. We now assumed sort of, it's like a game between the firm and the population. The firm deploys, the population responds. It's like a stackable game. And the firm tries to optimize through the response of the population. It's finding a stackable equilibria from the perspective of the firm. But you can now also reverse the order of play in that game. So what if individuals anticipate the use of their data for learning? And the reason they care is, again, performativity, right? Why would you care about the prediction of a model? Because they impact your outcome. Right, you have that in a lot of settings. And so I want to talk a bit about this perspective and how populations can impact models through data, which is of interest if there is performative effects of the model. So just some examples. Uber drivers, for example, care about the predictions that the models make about prices or demand or whatever led to the prices on the platform. So they were organizing and tried to strategically behave to sort of impact the algorithm, because the algorithmic predictions are important for their revenue and existence. We've seen like the reported cases for Didi drivers. More than 40% use third-party apps to coordinate and somehow strategize against the apps to get higher paying rates, right? So this is I think it was originally in China, also a ride-hailing app. They expanded more globally recently, but it's also a huge platform. There is concerns about labor conditions on these gig platforms, and that's why we see this sort of activism, digital algorithmic resistance, as we call it, or digital activism. Also, for example, in recommender systems, in Spotify, there's like a bit of a huge debate about these recommender systems amplifying existing inequalities in the music industry. And they try to, there's a Justice at Spotify campaign where they try to like stand in for better conditions, because the algorithm really polarizes the music industry. So what's important here, if people want to be effective against algorithms, is that they need to coordinate. So they need to coordinate and they can strategically use the data. And different areas that have been studied in that context is data leverage, data strikes, algorithmic collective action, and also there are different infrastructures in place where people can use to sort of coordinate. And the point is that a single data point has little influence on a model. And if you want to plant systematic patterns in a statistical learner, you need like more people that coordinate. I think that's I just want to spend a few slides on the effectiveness of these strategies to then go back and talk about the full loop again. So a way to model such strategies is that you have a population of individuals sampled from a distribution. You assume a fraction of them engage in collective action. So that's a model from a specific paper, but I think it's useful just as a simple abstraction to talk about it. The platform observes the mixture and then optimizes on it. And now you can ask several questions about how effective these strategies are, how many people do you need to implement them. You could have different goals. So in general, the goal is to have a favorable property of the model as a collective. So you could, for example, anticipate retraining as a collective. Anticipate that the model will be retrained on the data. And if you have a gradient-based learner on the other side, you can show that if you want to achieve a certain target model, theta star, the size of the collective that you need is proportional to sort of the suboptimality of your model measured in the norm of the gradient. It's a very sort of obvious or kind of natural result that you sort of, if you want to steer the model, you need to be able to control the direction of the gradients. And that's sort of the size of the collective you would need. You can also look at sort of more concrete strategies like planting a signal, for example. So if you have a statistical learner, you can add in correlations between X and Y that you would hope the model to pick up on. So here, planting a signal means that you want to, there's a function G, and you at test time, you want to be able to apply G to your data points and get the target prediction that you were hoping for. And success probability is the probability that you manage to do that across the population. And you can again bound the alpha that you need to be successful in such a case. And here it's proportional to the uniqueness of the signal that you're trying to plant. Sort of interesting if the goal that you have, the change to the learner that you want to implement is something that has low signal in the base data. So for example, you want to modify data points in a certain region of your domain where you have little support, you need smaller collectives. If you try to modify something in the whole bulk of the population, you need a much larger collective to plant new signals that are actually overpowering existing signals and the model will pick up on. So there's, yeah, this interesting lever that you have, and the fact that it is a learner gives you a nice, interesting algorithmic lever. Yeah. So you can also think of this, the uniqueness of a signal. It's somehow the strength of the signal in the base data. So how much you're conflicting with like an existing objective. We want to talk about that a bit later in the discussion. But the point here is that you can anticipate retraining as a population to get the model that you want through the data you report. And yes, small collectives can be effective. I mean, you can empirically look at that. If you want to plant a trigger, for example, if gig workers, freelancers want to plant a certain signal in a CV that makes them be classified a certain skill, against the BERT classifier, you need like very little data points to achieve that. This is not surprising because we all know about data poisoning and all these sort of attacks. And it has been shown that with small modification, you can really change models a lot. I think the point I want to make here is that data poisoning is like a very adversarial perspective. You assume that there's the firm optimizing objective, and then there's this adversary from the outside that you want to protect against. In that case, it's a bit different because it's just competing objective of two players in like an economy. And I think this perspective also gives rise to different assumptions and strategies that you would design because you actually care about, you don't want to just, you're a user of a platform. You don't want to completely arbitrarily report bad data or behave. It's just not useful for you. So there are a lot of interesting trade-offs at the level of incentives once you put that in the full loop. And I think an example I want to make here to just show that these things are very interesting because there are some small strategies you can do. For example, in a sequential recommender, it's a transformer-based sequential recommender system on Deezer, like Spotify, one of these music recommendation engines. And by just reordering playlists, putting a song that you want at a very specific position instead of a random position, you can have quite a disproportionate influence on these recommenders. So this is like example from a result. So Deezer is releasing one of their models that they used in production, which is nice. So you can play around with it. And you can show that what we did here is sort of the Spotify million playlist recommendations. And then in the playlist, you just in a very targeted way place a song. And you can show that if you place a song at the probability 1%, you get way more recommendations than an average song at probability 1% gets. So there's a lot of lever you can have just by these small modifications. And what we would want to have is small modifications that are utility preserving for the agents at training time. And at test time, you get the performative effect that you want. What's also interesting to see here is that no one's actually doing that in these data sets. So there's none of these like outliers in the songs. So train test is sort of all about the same for the songs. Good. Yeah, I talked a lot about incentives because I think this is a very interesting, like, also future direction for understand a bit more these sort of competing objectives and the utilities and costs at the different participants. So these actions come at a cost. They're not self-incentivized. So, oh, there's a year missing. So there's famous work about collective action in a more general setting that's usually it's not self-incentivized because you need some seed costs to get it run. Everyone would benefit if everyone does it, but it's sort of a dilemma and no one would actually start it. And then firms would also might to protect and punish against it. So there's a lot of incentive to find some good solution that's Pareto optimal in some sense in these markets, which I think is interesting, which I haven't seen like worked out in that context of statistical learners. Yeah, and it's again the performativity that plays an important role here because it determines the payoff of the strategy. Your effect on your own outcome depends on the performativity of the predictions that you have impacted through your data, sort of closing the loop. Yeah, this was a bit more like zooming out. We have another few slides about potential directions. We have, okay, I also have this very high level discussion summary. Maybe I should do that first. Okay, so going back about what we've discussed. So we've mentioned that deploying model in the real world, they are part of a broader socio-technical ecosystem. And performativity is pervasive. So these effects are like everywhere in almost all social economic prediction problems. Still, and it's kind of fundamental importance to bring them into machine learning. I hope we have convinced you of that. Performative prediction is like interesting abstraction to talk about these problems, and there were a lot of questions coming up. So it's like a very fruitful and interesting direction to think about. Yeah, changing prediction means changing outcomes, and solution can't. Pure prediction is no longer a purely technical endeavor. So there is this dimension of power, behavior, individual interests, incentives. It's just like there are a lot of other aspects that become relevant for the very theory of machine learning and prediction. And solution concepts can be context dependent because you can solve the same optimization problem in a different context and you get different solutions. I think these are some of the key, more high-level takeaways. And we really hope that performative prediction offers some conceptual tools, some theory to articulate these questions in the first place. I'm convinced that when going into more specific cases, you need more than just a d of theta. You need to have domain knowledge. You need additional modeling, as Tijana presented it. But just the concept and how it enters the ML pipeline, I hope this comes out from the framework. Some open problem and challenges. Do you want to, I mean, one of the major things is data, right? The availability of data. It's very hard to test these algorithms. We can't play around with actual performative systems, right? These are like the systems that policies, these are systems that firms deploy. It's really hard to play around with it. So one thing that we usually do is we resort to semi-synthetic settings. So we take data and we simulate performativity on top. And that's how we simulate algorithms. With the power meter experiment, we were trying to get some empirical insights, some data to kind of talk at least about the strength of the effect. It's still very different to actually deploy an algorithm in such a context. So yeah, I also think whenever you collect data, it's very important to also collect predictions to at least have something to work with. If you then want to talk about performativity later, I think, for example, in recommender system data sets, it's very important to have also access to the recommendations and not just the clicks and the search queries to sort of do research in that field. I want to hand it over to Tijana because she wanted to be. What's the plan? What's the plan?
No, it's okay. I guess we put some points because we weren't sure how lively the discussion was going to be. So we wanted to have like a few points to just see the discussion. But I think people have brought up a lot of interesting points. So
maybe this was even not necessary. So yeah, anyway, these are just some problems that we think are pretty important to think about in this space, and we still don't have very good answers. So Celestine mentioned the issue of data availability. That's definitely like a big obstacle and kind of like pushing this whole agenda forward. One issue that we didn't really touch upon, but it is pretty important when talking about optimality. So we saw that in these algorithms that we talked about that try to optimize the performative risk, we need some amount of exploration of models. And in practice, it's not like if these models are like super consequential that you can just arbitrarily explore models so that you learn enough about your distribution map and you learn how to optimize the performative risk. You need to do so in some way that's safe, both for the environment, but also for the learner. So the learner is not also incentivized to deploy just completely arbitrary models. So is there a better solution concept that maybe we should be shooting for that would be feasible even with some kind of safety constraints on the exploration? Yeah, then we have a very high level point about how performativity should be regulated. So Celestine talked about competition. There are definitely certain aspects of digital economies that that are regulated, but performativity just comes in many different shapes and forms, and I think we still don't have a pretty like general and robust framework to talk about regulation in performativity. And finally, we saw these like two competing models at the beginning of the talk and at the very end of the talk. In the first part, as Celestine mentioned, we had this model where we deploy the model and then the environment is impacted by the model. In the last part, we had basically a reverse model where people choose their data and then the model responds to people's data. And so both kind of feedback loops make sense because of the incentive structure, but we still don't have a general modeling framework where we can talk about both of these influences simultaneously. And so figuring out the right language to talk about that would be very valuable. So yeah, I think that's all we wanted to say. Thank you so much for your attention, and we're happy to take for questions.
Yes.
I have a question on the first part. So I work a lot in healthcare, and this is, of course, very relevant. We deploy models. For example, when we do clinical seizure support, we will reconstruct the given patient. Right? For example, with the risk score. My question is, why do we want performative? So we are all very used to the idea that we want to improve performance, and this idea that the rating will improve performance was very natural to machine learning. But so at the beginning, we've seen examples where if you improve performance, things actually get worse. Right? The example you gave about the coverage score. But there are also examples in healthcare where you actually don't want to. So for example, a simple example, you have a population of patients and you want to give a risk score such that the patients that are easy to classify are progressively showing up less and less in the score because you either treating them well, so they don't get the condition, or you're referring to a specialist. So your problem will get harder over time because you will only be left with the hard patient. So in that scenario, one would argue you actually want to see your performance go down to know that it's improving the outcomes. So again, it ties back to the last part of the talk where we really want to look at it because of the facts. If we have reflection on this starting intuition that we want to iteratively move performance, is that really something we want to subscribe to?
Okay, so the question was about performativity in healthcare. Yeah, I completely agree. I think often the very purpose of predictions in healthcare is for them to be self-negating. You want to identify people at risk, and then you want to treat them and like reduce the risk. It's like very often you actually want that your prediction at hindsight doesn't look maybe accurate. So performative is relevant. The purpose is that your predictions have an effect. You want that, right? The solution concept. I mean, I think you would have to think about how to define the loss function and the objective in that case, right?
Yeah.
You will not put accuracy as an objective that you care about if you think about it in the If you just do accuracy, you ignore performativity and you do retraining, something maybe disastrous will happen. But if you now aware that there is performativity, so you should factor theta in when choosing your loss function. It could depend on the data. Maybe it's just the outcome that you care about of the patients, much less than the prediction. So this would be a more well-posed problem in that context.
Yeah, I just want to like say that, yeah, I agree with that. I think that in your example, I think you exactly want to optimize the performative risk. I think you want to find like a decision rule that will be somehow optimal for some welfare notion. I think the question is just that, what is your loss function? And I think the loss function is not just a predictive measure. And I think that that's very important, but you need to regularize by some of these other considerations that you mentioned. So
Going on to that question, so I agree that in certain settings, just optimizing some outcomes and utility could be way more relevant than accuracy, right?
yeah, absolutely.
So if you remove this data dependence from your loss, then it's just some outcome Y. To what extent is performative optimality and functionality and stuff still relevant?
Performative stability won't be relevant because performative stability won't be meaningful, but performative optimality would still be meaningful. It's basically just saying like, I want to pick, like if my loss only is some property of my data distribution. Like I want my data distribution to be in a particular, part of the space because I know that if it's around there that, people are happy in whatever notion of welfare you have. You still do want to find a theta that will take the distribution to that part of the space, all right? I just think, the stability part won't make as much sense.
So how to find it?
Well, it depends. I mean, you can think of it like in a very general setting, like you can think of it as a bandit problem. Like I can just explore a bunch of different thetas, try to put confidence bounds on the welfare for each theta, and then like run some kind of bandit algorithm. Now, of course, I mean, as Celestine said, like I think you really need to think about the particular application you have in mind. And ideally, you would try to like model something about this feedback between theta and your data distribution. So yeah, I think it's a little bit hard to say anything without further assumptions.
Yeah, maybe something I would like to emphasize. So I mean, solving performativity would mean solving all of these very fundamental questions in econ game theory. It's just area, right? That's not our ambition. I think performative prediction is meant to be, we started from risk minimization. There's this limitation that you can't account for this very fundamental concept of performativity. And we try to find the simplest abstraction to talk about this concept and understand how it comes into the data-driven pipelines that we're using, right? It's more of there are a lot of very interesting things, right? Suddenly like power plays a role. Suddenly there's a distinction between two solution concepts. Before we just had optimality being optimality, right? There's this notion of steering. There's, it's just like conceptually, I think it gives you a language to talk about these questions. I think solving it in full generality is like an over-ambitious goal. I really think the healthcare application, I mean, I'm not like a healthcare specialist. Like people in that domain know much better what the impact of their treatments is, right? You need to go into the domain. But if you talk to a machine learning person, that's sort of some translation of what's happening to the language that they work with. I think performative prediction can be useful for that. Yes, Nicola.
Yeah. To the last question, the effect of the predictions on users and the users of predictions, right?
Mm-hmm.
So, is this an example of a bilateral problem, or again, it's part of the game? Again, the repeat is part of the game. This is what we're talking about. How is this different from that kind of frameworks?
Yeah, maybe just before we answer the question, I just want to be mindful of people's time. Like we're past times. If people want to leave, that's totally fine. We're just happy to take more questions. Don't feel like, yeah, like don't feel obligated to stay for any of this. Yeah, I think that's a good question. I think that there are two, I would say like that last point has two questions baked in. One is the question of, yeah, how do we solve the underlying optimization problem, which I think is what you're getting at. But I think the other thing is conceptually, it's not even clear what is the right, perhaps equilibrium solution that the system should converge to, because as Celestine said, it's kind of like a stackable game. Like the first performativity is like a stackable game where like you deploy theta, then D best response. Now, in the collective action part, we talked about this model where you first pick like a D and then theta best response. Yeah, is conceptually the right thing to look at some like Nash between D and theta. I think it's just not clear what the right like equilibrium is in this concept. But if it is some kind of Nash, then I believe that what you're saying maybe would be, yeah, the right thing to do.
Yeah, and I just reiterate, I think one very interesting conceptual point here in this game is this contrast between micro and macro, that you have the individuals and then the individuals in aggregate impacting the learning algorithm. It's again the distribution that feeds in. What matters for the learning algorithm is the distribution, the aggregate distribution that sort of comes about from individual behavior. And then you have this aggregate thing feeding into the learning algorithms, coming into a parametric prediction that's some sort of, it's not an individual prediction, there's some sort of coupling, and then you again have the individual responses. I think there's like something really interesting here to understand better. That's just something I'm fascinated about in that loop as well, which I find interesting. High level optimization problem. Yes.
I'd like to ask you a specific approach from the data perspective. So can you shed some light specifically on if the performance predictive model deal with like black events, which is more destructive events, where it is basically random model unused. Is that
sorry, are you saying something, are you referring to like some exogenous events that are not, like some shifts that are not coming from performativity?
irregular and very intensive. And just recently innovation, your assumption that the model is basically shifting, of course not shifting, but shifting slowly.
Yeah.
As you in the real world data, you see a lot of data, a lot of events that happens very rapidly and unexpected. And most important, not very irregular. So that's makes things very difficult for you to make a right prediction. I'm wondering if the methodology help to deal with such events.
Yeah, I think that's a very good question. So I think that's related to a question that we maybe had somewhere in the first part of the talk. So I think, yeah, this model doesn't really handle those kinds of like exogenous shocks, but I think it would be very interesting to consider a model that can handle, there would be like a combination of like standard online learning where your, you know, environment can change arbitrarily at every time step. But you also take into account the fact that, you know, some of the shifts that you're observing are caused by performativity. So they are coming from this kind of like endogenous effect of deploying a particular model. Because in the example that you're giving, performative optimality wouldn't even necessarily be well defined, right? Like if I have these like shocks at different points in time, then I maybe don't want the performative optimum in those times when there's a shock, right? But I want to somehow be able to adapt to those changes. So yeah, I think it would require maybe like some more like an online notion of performance in that case.
My second question is actually how relates to this generalization issues that come out. Can I say in my imaginary world, I have a perfect model that can deal with all of things. Then we don't need any, you know, the performance predictions and what performance predictions.
I don't know if I understood the question. Vision.
Let's,
Yeah, I
let's-
just,
let's
just,
just
want-
we'll be
yeah,
here
yeah,
for
we'll
a
be
few
here.
minutes.
Yeah, yeah,
Go out for lunch.
yeah. I don't want to.